Good morning. We are going to start with the conference. The first talk is from the Professor Sumit Kumar Sharma. He is in this session. Carol, good morning.
Good morning, Professor Javier. It's nice to see you.
Mucho gusto.
Saludos.
Professor Milan, good morning.
Oh, I have afternoon, but for you, good morning.
Okay, it's correct. Professor Sumit Kumar Sharma, please. Present your talk, please. Okay, Professor.
Hi everyone. I hope I'm audible.
Yes. Come on. Begin, Professor Sumit, please.
I cannot hear anyone. If
Yes,
you can
Dr.
hear
Sumit,
me,
you are audible. You can start with your presentation. Yes,
okay,
you are
fine.
audible. Yeah, thank you.
Okay. So first of all, thank you for the organizers for inviting me to deliver a talk in this conference so that I can communicate my work that I had done in the recent time with you all. So the title of my talk is Recent Development of Frames in Quaternion Hilbert Spaces. So this talk will contain in the talk I will be discussing about frames in Hilbert spaces. Then I will be give you brief idea about quaternion Hilbert spaces. Then I will talk about the frames in quaternion Hilbert spaces. And then the recent development that we did in the direction of frames in Hilbert spaces. In the recent development, I will be covering with woven frames in quaternion Hilbert spaces and fusion frames in quaternion Hilbert spaces. Then we'll be talking about woven K-frames in quaternion Hilbert spaces. Then I will be discussing the definitions and examples of K-fusion frames in quaternion Hilbert spaces. And then finally, we'll be talking about frame of operators in quaternion Hilbert spaces. So these are the recent development that we had worked together in recent times. So as we all know that it's already been discussed in the last sessions that the topic of concept of frame theory was actually introduced by Schoffer in 1952. Then in this landmark paper by Dobschies, Grossman and Mayer in 1986, they actually reintroduced frames, and they observed that frame can also be used as a series expansion of functions in L2R. And later in 2001, R. Young actually wrote a book in which he actually reintroduced frames, and at this juncture, researchers actually... Hello?
Yeah.
Researchers actually reintroduce frame theory. R. Young reintroduced frames in this book, and then researchers got an idea, and most of the work actually started after this book. So what was the formal definition of the frame? Frame is a sequence in a Hilbert space. A sequence is said to be a frame if we have a positive constants A and B which satisfy this inequality. A norm of x square is less than or equals to summation mod of inner product xn is less than or equals to B norm of x square. X belongs to Hilbert space. The positive constant in this inequality A and B referred to as in lower frame bound and an upper frame bound. A is referred to as lower frame bound and upper frame bound. And a frame is said to be tight if these constant A and B are same. And we refer the frame as a Parseval frame if these constants happens to be same and equals to the 1. So if only the right hand side of this inequality is satisfied, then we say the sequence is a Bessel sequence. So this was the definition of frames in Hilbert spaces. Now I will give you a small idea about field of quaternions. So field of quaternions is actually a non-commutative field, and it consists of all the vectors of the form x0 plus x1i plus x2j plus x3k, which satisfy these conditions. And actually this is a division ring. So it is a non-commutative field. So if we choose a non-zero quaternion, then the conjugate of this quaternion is defined in this manner. If this is a quaternion, then its conjugate is this. And the modulus of this quaternion is defined to be the under root of x0 square plus x1 square plus x2 square plus x3 square. And the inverse of a quaternion is actually conjugate of that appears to be this. So it satisfies all the properties. This space having all such vectors where xi belongs to R satisfies all the properties of a non-commutative field. So that's why being in non-commutative in nature, there are two types of quaternic Hilbert spaces that do exist. One is right quaternic Hilbert space, another is left quaternic Hilbert space. Because they do not commute with each other, therefore they depict different structures, although the structures are isomorphic. Therefore it's better to work in a particular direction in one of the field, and that we had covered. We had taken the right quaternic Hilbert spaces. So right quaternic Hilbert spaces are actually the Hilbert spaces in which vector spaces of over the quaternions which satisfy following properties, that this inner product is equals to this conjugate and all those properties. And as it is the right quaternic Hilbert space, so only the right part of this inner product do exist. So if we look into the examples of right quaternic Hilbert space, then one observe that easiest example would be if we take collection of all quaternions, and then it will be a right quaternic Hilbert space over itself. And then this is an m-dimensional quaternic Hilbert space, right quaternic Hilbert space, in which we had taken a collection of n tuples, and it forms in right quaternic Hilbert space with the inner product defined in this manner. So this is an m-dimensional right quaternic Hilbert space. And then if we look into the example of an infinite dimensional, separable infinite dimensional quaternic Hilbert space, then we can define L2H, and by defining by choosing all those sequence of quaternions which satisfy this inequality, the series summation is finite, then we define the inner product in this fashion, then this also satisfies all the properties of right quaternion Hilbert space, and this actually defines an inner product. So this is an example of separable quaternion Hilbert space. So we defined a frame in quaternion Hilbert space, and the definition is this way: if we choose right quaternion Hilbert space, and then any sequence in this is said to be frame if it satisfies this inequality. So in a similar manner, the constant A and B are called the lower frame bound and upper frame bound. And frame in a right quaternion Hilbert space is said to be tight if this constant A and B happens to be same, Parseval, if the constants are same and equals to 1. And exact, we say this is exact if we remove any one of the element from the sequence, then it's no longer be a frame for the right quaternion Hilbert space, then we say it is an exact. So if we look into the examples of right quaternion Hilbert space, so if we take any orthonormal basis in right quaternion Hilbert space, and if we define the sequence ui as ui is equals to ui plus 1 is equals to zi, then this actually a frame for VRH, which is tight and non-exact, and bounds happens to be 2. And if we define a sequence ui as ui is equals to zi and ui is equals to zi minus 1, then ui is a non-tight and non-exact frame for right quaternion Hilbert space. And if we define a sequence ui in such a way that first term of the sequence is exactly equals to zi and uik is equals to uik plus 1, uik plus 2 is equals to zi by under root I, then this is a Parseval frame for VRH. And one may observe that itself an orthonormal basis are always an exact frame for VRH. So now if we come on to the development that we covered in this talk is Bhuvan frame for quaternion Hilbert spaces. Bhuvan frame for separable Hilbert spaces is actually introduced by Bambrose in 2016. So motivated from this paper, we defined Bhuvan frame for quaternion Hilbert spaces. Bhuvan frame from quaternion Hilbert spaces in 2021. And in this, we actually define Bhuvan frame in this manner, that if bracket M is the sequence of first M natural numbers and VRH be any right quaternion Hilbert space, then the sequence Ui, J, I belongs to and J belongs to bracket M, be a family of frame, then this family is said to be Bhuvan. The universal positive real numbers R1 and R2, so that every partition this chosen of natural numbers, the family this is a frame for VRH with the same lower bound R1 and R2. So each family that we are defining here is referred to as weaving. If every weaving is Bessel sequence, then we say this family is a Bhuvan Bessel sequence for VRH. So if we look into the example of Bhuvan frame, so if Vi is any frame for VRH with a bound R1 and R2, and if we choose any sequence of quaternions satisfying the property that infimum is bigger than a positive number and supremum is less than another positive number, then this family defined in this manner: Uij is J, Vi, I belongs to N, J belongs to bracket N. Then for any partition, whatever we choose, we can able to find out the bounds R1, R3 square and M2, R2, R4, such that any partition chosen from this is makes the sequence as a frame for the right quaternion Hilbert space. So this family that we have defined here is a Bhuvan family. So if we look into an example where the family actually is not a Wu1. So if VRH be if we choose a VRH be a three-dimensional quaternion space with orthonormal basis E1, E2, and E3, then if we define a family U1, F1 is equals to E1, E2, E3, and F2 is equals to E1, E2, E3, E3. Since if we pick any element from VRH, then this inequality would be satisfied, and this forms a frame for VRH. Similarly, we can prove that F2 is also a frame, but which does not form a Wu1 family, as if we choose a partition sigma is equals to 1, 2, and U is equals to E2, then we are not able to find out the lower frame condition. Therefore, this family is not Wu1, but actually these two are the frame. These are frame, but not a Wu1 family. So in this manner, we actually define right quaternion Hilbert space. This space is actually helpful for us to define a frame operator, which actually give us the reconstruction for a Wu1 family. So this manner, we defined an operator FP from this Hilbert space to VRH by defining the operator in this way. Then this operator we refer to as a synthesis operator for Wu1 family, and the adjoint of this operator we refer to as an analysis operator. And by combining these two operators, we can able to find out the Wu1 frame operator. And actually, with the help of this operator, we can able to reconstruct the operator and able to reconstruct the vector in right quaternion Hilbert space. So there are few results that we had actually I had included some of the results that we able to prove that we can able to construct an Wu1 family with the help of existing Wu1 family. If this is a Wu1 family, and if we able to choose if there is a bounded linear operator on VRH, then TF is also a Wu1 family. If and only if T is a surjective. If this operator is surjective, then TF is a Wu1 family. So this is how we can able to construct an Wu1 family with the help of existing Wu1 family. And this says if Tj's are the operators which define to be positive linear operator, then this family is also become an Wu1 family. So now we come on to the next development. Although the definition of fusion frames we had already covered as in consequences of frame operators that I will be covering in the last, but actually an fusion family was studied by Geeta and Kutniok for Hilbert spaces. And after defining this fusion frame as in consequences of frame of operators, an exhaustive examination of fusion form within the context of quaternion Hilbert spaces we covered in this paper. So in this, what is a fusion frame? Fusion frame is a collection of right subspaces of right separable quaternion Hilbert spaces, and Vi is the family of weights. So if pi I is a projection on Wi's, and if this inequality is satisfied, then we say this is a fusion frame for quaternion Hilbert spaces. So this is an example for fusion frames. So if we construct a right Hilbert space by taking the orthonormal basis and constructing the right linear span of each vector, then the collection of all these spans over the weight Vi's form then fusion frames for R1 and R2. So in fact, this is also an existing result for existence of fusion frame family. This says if UJs be the frame sequences in VRH with the frame bot R1I and R2J, and WI are the spans of this frame sequences, and EIJs be the orthonormal basis for WIJ. And suppose this condition is satisfied, that the infimum of all this is positive and supremum is finite, then UI, VJ, WI is a frame for VRH. If this is a frame, then this family becomes a fusion frame, and converse is also true. So this is an equivalent condition for the existence of fusion frame. Then we studied about the Wu1 fusion frames. This says if we have two fusion frames, HIRVI and WIRWI, the two fusion frames for VRH, then these family H and W are said to be Wu1 fusion frame for VRH if there exists a constant R1 and R2, and any subset for any subset sigma of I, the family of this union is a fusion frame for VRH with the lower and upper fusion frame bounds R1 and R2 respectively. And this is an example of Wu1 fusion frame. If we choose orthonormal basis to be EI and we have U is equals to, then we can able to write an every vector with the help of this orthonormal basis. And if we define HIR subspaces with the span of EI plus 1 and WIR with the span of EI plus 1, EI plus 2, and choosing the weights to be equals to 1, then HRI, VI, and this are the fusion frames with the fusion frame bound 1 and 2 and 1 and 3 respectively. In fact, they form a Wu1 fusion frame for VRH. Now, the next study that we did in this direction is Wu1K.
Professor Sumit, you have 2 minutes, please, for finish your talk. Come on.
Then I will. Okay. So next development that we did in this direction is Wu1K frames. In fact, this talk, this Wu1 frame for Hilbert space was studied by Gavruta and then later by Elozov. Then in this paper, we had studied Wu1K frames in quaternic Hilbert spaces. And then this is the definition. Actually, I am running out of time, so I have to cover many more. I'm skipping this. The next we studied about K fusion frames in quaternic Hilbert spaces. And this study for Hilbert spaces was done in this paper in 2018. And then in this paper, we introduced and studied K fusion frame in quaternic Hilbert spaces. So this is actually the definition. Now, finally, the frame of operators in quaternic Hilbert spaces was actually the generalization of G frames in Hilbert spaces. And this was studied by Sun. And then in this paper, we actually define frame of operators in quaternic Hilbert spaces. So this is the collection of operators which satisfy this inequality, then we refer to as a frame of operators. So this is an example of frame of operators. And actually in this example, we had observed that this is the most general form of frame of operators, is actually more general concept of frames. Once we have a frame, then we have a frame of operators. And then here we had explained that once we have a pseudo frame, then also we have frame of operators. And then if we have a bounded quasi-projectors, then also the space has the frame of operators. And finally, the frame of if we have a frame of subspaces, then also we can able to construct an frame of operators with the help of fusion frames. So these are the references that I had covered in my talk.
Thank you very much, Professor Kumar. Any questions? No? Okay. Thank you very much.
Thank you, sir.
Next talk is from Professor Barinder Kumar. Please.
I think the next talk is from Dr. Dilip Kumar. An updated program is sent in the evening, I think. Dilip, are you here?
Dilip Kumar.
Yes.
Yes, sir. Am I audible?
Yes, you are audible.
Thank you, sir. So,
Okay.
let me share my screen. Okay, so is it visible to everyone? My screen is visible to all?
Yes, Dilip, go ahead.
Okay.
Okay, thank you, sir.
See.
So, good morning, everyone, and thank you for this opportunity to present my paper on generalized variation diminishing wavelet using Hartley kernel and Bose transform. This is a joint work done with joint work done with Dr. Nikhil Khanna, Professor Shiv Kumar, and Dr. A. Jotan Sangha. So it is a collaboration work on the topic of generalized variation diminishing wavelet using Hartley kernel and Bose transform. So introduction. So wavelet theory originated in 1984 for seismic signal analysis, involving significantly with contribution from Grossman, Mollet, Mayer, Marlet, and Dubishes. So the key developments before our work were like multi-resolution analysis by Mayer and Mollet, and a compactly supported orthogonal wavelet by Dubishi, an introduction of variation diminishing wavelet utilizing convolution transform by Pathak. So for before that, we will look at the Hilbert transform. In 1912, Hilbert introduced an integral transform called Hilbert transform. And from that, the analytic signal was proposed by Gabor in 1946, which plays an important role in the communication field, especially optical analysis, image processing, and signal processing. So the classical Hilbert transform was further generalized to the fractional Hilbert transform by Lohmann in 1996. And the Bose transform of a function f belongs to square integrable function is defined by this expression. This is this expression. We define Bose transform using this expression. So there is a relationship between Bose transform and Hilbert transform of a function, which is given by this relation, where G is the kernel function, defined by this expression. And we define, let us define the operator B theta on L2R, where B theta is equal to cos theta I plus sin theta, or Bose transform. So where theta lies between minus pi by 2 to pi by 2. So where B theta is called a fractional Bose transform. And if we put theta equal to pi by 2, then fractional Bose transform. So B theta is called fractional Bose transform. And if we put theta equal to pi by 2, we will get Bose transform, fractional Bose transform will be equal to Bose transform. So we have worked it on wavelets. So what are wavelets? So wavelets are mathematical functions that cuts up data, function, or operators into different frequency components, and then study each components with resolution matches to its scale. And they have advantages over the traditional Fourier method in analyzing physical situation where the signal contains discontinuities and sharp spikes. They are capable of providing time and frequency information simultaneously, hence give a time frequency analysis. Unlike Fourier transform, wavelet transform are locally based, which can give more precise information of the signal. So some example of the wavelets are, the simplest example is the Haar wavelet, which is the first example of wavelet and given by this discrete type of function. And this is a kind of Haar wavelet is discontinuous, and it is a discrete wavelet. So after that, Dubishi also invented some wavelet, and after that, so many wavelets were discovered. So this is the basic example of the Haar, which is called Haar wavelet. So in our work, we in our work we study the generalized wavelet, focusing on variation diminishing wavelet. We work on variation diminishing kernels. So generalized wavelet with specific changes of sign, and generalized wavelet based on Tanos kernel. So we work on that, and what we have achieved is generalized wavelet that expand the application of wavelet theory and the exploration of Fourier transform properties of wavelets, specifically those based on Hartley kernel and Gauss transform. And our basis of research are utilizing the foundational work on convolution transform of transform to advance the study of wavelet. And we provide new results and insight into the structural and application of wavelet in various domains. So some definitions. So definition, variation diminishing kernel. So this is the definition of variation diminishing kernel. Let psi be a continuous and bounded function, and let kx belongs to L1R, and let fx equal to k star psi of x, which is given by this integral. Then the kernel kx is known as the variation diminishing if n of k star psi is less than n of psi, where n of psi denotes the number of changes of sign of psi on R. And kx is the variation diminishing if and only if k hat n given by this expression, where this L and M and L is greater than 0, and M and Dn are real number, where with 1 upon Dn square, summation 1 upon Dn square is less than infinity. So we define this variation diminishing wavelet if this condition, if k satisfies this condition, such that the Fourier transform of this is given by this expression, and this gives kx equal this gives kx equal to this then this gives this kx equal to this result, and after that we then ksx is given by this expression, whereas belongs to positive integer. Now let us define ksx by psi of x, where kx is the degree of kx be the degree of p. Then psi of x given by this expression, and it has exactly s changes of sign for s equal to 1 to p minus 1, where p is the degree of kx. So let psi be a wavelet. Then for a variation diminishing kernel, k given by this expression 2, this expression of variation diminishing kernel given by 2, where for this is called variation a real number, and 1 upon dn square is less than infinity. Then if we take convolution of psi with k is again a variation diminishing wavelet, is known as variation diminishing wavelet. Hartley kernel can be expressed as cos of x equal to cos x minus cos beta x, which is equal to sin x plus sin beta x. And the Hartley-Bose-like wavelets are defined by Hartley-Bose-like wavelet of psi x equal to psi x plus minus psi beta Bose of x. So there is a proposition. Let psi be a wavelet such that psi and psi hat belongs to L1R and psi hat 0 equal to 0. Then Hartley-Bose-like wavelet of psi of x is again a wavelet. So excellent. So Tano et al. Investigated the following class of convolution transforms. So these are the let f that is given by this expression, where nu and dn and pn are real numbers, and dn upon pn lies between 0 to 1, and this condition, like 1 upon dn square is less than infinity, summation 1 upon dn square. One may choose pn equal to infinity if dn greater than 0, or pn equal to minus infinity if dn less than 0. Then this gives this expression, which is equal to 1. So we further assume that psi1 equal to maximum of dn where dn is less than 0, and psi2 sigma2 is equal to minimum of dn where dn is greater than 0, and beta1 equal to maximum of pn where pn is less than 0, and beta2 is minimum of pn where pn is greater than 0. So what we have got are these are the result that we have got. Let psi be a wavelet such that psi and psi hat belongs to L1R and psi hat 0 equal to 0. And let K belongs to L1R be a variation diminishing kernel, then Hartley-Bose like wavelet of psi star K is again a wavelet. This result we have got, and after that we got this result that Kx be a variation diminishing kernel, and let psi x equal to Ksx for s greater than 0. We define by the expression 4 such that psi and psi hat belongs to L1R, then Hartley-Bose like wavelet of psi of x is a wavelet which has exactly s sign of x changes of sign. And if psi x is defined by the third expression 3, then Hartley-Bose like wavelet of psi of x has at most s changes of sign. So next result that we have got is let fz be defined in expression 5, and z is a complex number where psi and rho is the real and imaginary part. And if we take rho such that real part equal to beta 1 plus sigma 1 by 2, and beta lies between beta 1 and plus sigma 1 by 2 and beta 2 plus sigma 2 by 2. And rho, if we take minus infinity to infinity, like imaginary part can be any number. Then if we take modulus, then inverse of modulus of fz is less than inverse of modulus of f of that or the real part that we have got. And sorry. And the next result that we got, let that if psi be a let psi be a wavelet such that psi and psi hat belongs to L1R and psi hat 0 equal to 0, and let f of ix inverse of f of ix be the Fourier transform of some function kx belongs to L1R. Then for b1 plus sigma 1 less than equal to 0 and b2 plus sigma 2 greater than equal to 0, Hartley-Bose like wavelet of psi hat equal to k convoluting with Hartley-Bose like wavelet of psi is again a wavelet. So this if we convolute k with the psi where k variation diminishing kernel, then this expression again give a wavelet. So the next result that we have got is let psi be a wavelet associated with the scaling function. Let psi be a wavelet associated with the scaling function phi such that psi and psi hat belongs to L1R and psi hat 0 equal to 0. Then we got this result. Then we got this result. And next result that we have got, let psi be a orthonormal wavelet such that psi and psi hat of L1R and the psi hat 0 equal to 0. Then s of nu equal to this summation this expression. This expression, then s of n is well defined and finite. Or further, for any integer I of length 2 pi in R, if we integrate s nu d nu, then this integral will be less than 8 pi. So the conclusion is, so we introduced some generalized variation diminishing wavelet, and we constructed the construction is based on the Schoenberg's theory of variation diminishing kernel, the Hartley kernel, and the Bose transform. These wavelet generalized the variation diminishing wavelet introduced in one is our this paper RS Pathak variation diminishing wavelet and wavelet transform. So these are some references that we have used, and thank you. Thank you.
Thank you very much, Professor Dilip Kumar.
Thank you, sir.
Are there some questions? Nothing? Okay. Thank you very much, Professor Dilip Kumar.
Thank you so much, sir.
Next talk is from Cole Timothy, please. Okay, Professor. You can begin, please.
Is it my screen visible?
Yes.
Okay. Good morning, everyone. I thank all the organizers for giving me the opportunity to share my research in your conference. And today, the topic of my talk is the role of pseudo-Hermitian Hamiltonians in quantum information theory. And the work is based on, some new development in quantum information theory as well as in quantum mechanics. And the work is done together with S.K. Kaushik and Nikhil Khanna. So to begin my talk, let us recall a little bit of the postulate of quantum mechanics. See, in quantum mechanics, the few postulates are state space that is represented by Hilbert space. Like you can take it capital L square R, or you can take it the small l square z, and evolution. Another important concept is evolution. Here the evolution is described by the unitary operator. And another important concept is quantum measurement, which is described by a family of measurement operator. Now, when I say state space means maybe like this space, or maybe like this, or maybe like infinite settings. So these are state space, and any element belongs to here, they are called as state. And then evolution is a unitary operator from Hilbert space to Hilbert space. And we call it evolution because this nature is unitary, because it preserves the norm. So that means the information is preserved. So that's for that reason they call it evolution. And then the quantum measurement I will describe in the next page. Now, in quantum mechanics, one of the most important concepts is called Schrödinger equation. Here the state in the quantum in the Hilbert space evolve in time according to the Schrödinger equation, which is given by this formula. Here this small h is Planck constant and this h is the Hamiltonian. We call it Hamiltonian, or that is nothing but in mathematics we call it Hermitian operator. Now I had mentioned what is the quantum measurement. So quantum measurement are nothing but it is a sequence of positive operator and satisfying this condition. That is the summation. This lambda belongs to this n lambda, it should be equal to I. That is the resolution of identity. And in fact, this positive operator value measure is a general description of quantum measurement. Now, these quantum mechanics are usually, or it is built by probability theory. Now, the probability distribution of an observable, which is mentioned above here, in a state D is given by this formula. This is nothing but trace, and here this D is nothing but a positive operator whose trace is equal to 1. And this is the formula, this is the probability distribution given by this formula, that is given through trace. And then one of the most important equation in the quantum mechanics is called time evolution operator. Time evolution operator U is defined in this manner. In fact, this is derived from time dependent Schrödinger equation, which I have mentioned before also. And now this H is Hermitian operator, and this U is called, and this U is in fact a unitary operator. Now the question is, which is of interesting thing, is that what will happen to this time evolution operator U derived from Schrödinger equation if H is not an Hermitian operator. So this this observation in many of the dynamics in quantum mechanics, it is observed that the Hamiltonian H need not be Hermitian, and that is that is found through this experiment, and this is a very much the research is going on in this topic and where to go. Suppose like the time evolution operator which I have discussed above is based on an operator which is Hermitian, but now since there are some dynamics, or there are some the motion in the quantum mechanics which need not be Hermitian, so where to go about it? So now researchers look for operators whose condition is less than Hermitian to represent the Hamiltonian. And one of before I describe such an operator, let us look at some of one definition. A bounded linear operator is metric operator if it is positive definite, and this metric operator induce another inner product which is given by this formula. Now, one of the most interesting thing I have mentioned before, that in quantum mechanics the motion need not be some motion cannot be described by the Hermitian operator. So therefore the researcher has introduced a concept called pseudo Hermitian operator. This pseudo Hermitian operator is defined in this manner. A linear operator is said to be pseudo Hermitian if the adjoint of T is given by this formula. This is, if I take this rho to be identity, then this is nothing but is unitary. But they have given an operator which is slightly, whose condition is slightly lesser than the Hermitian. And another formula is an invertible linear operator is said to be pseudo unitary if it is satisfying this condition. Now, coming to our contribution, first of all, let us recall a definition. Let H be a finite dimensional Hilbert space. A pair that is theta j and pi j is called a bi-orthogonal pair of raised bases if it satisfies the two conditions. The first condition is these two has to be raised bases, and the second thing, they have to be bi-orthogonal. Next, we have given a spectral theorem for pseudo-Hermitian operator. It is analogous to that of the spectral theorem for Hermitian operator. I think all of you are aware of this spectral theorem of Hermitian operator. See, this H be a finite dimensional Hilbert space. This rho be a metric operator. And this is said to be, this T is pseudo-Hermitian operator if and only if there exists a bi-orthogonal pair of raised bases such that this is the eigenvector of T and all the eigenvectors of T associated to theta j are real. See, this is analogous to that of the Hermitian operator, but in Hermitian operator, it was categorized using orthonormal basis. But here we categorize using raised basis. And the consequence of this result is nothing but the decomposition of pseudo-Hermitian operator. All of us are aware of that decomposition of Hermitian operator. Analogous to that, we have given another decomposition, and which is very essential to study in the pseudo-Hermitian quantum mechanics. The result goes like this. This will be the metric space, T be a pseudo-Hermitian operator. Then there exists an invertible linear operator from here to here, from LJD to H, and a diagonal operator from LJD to D, LJD, such that it satisfies this condition. And it is analogous to that of that, but here, since this T is not Hermitian, the formulation is a little different, but the beauty is that Tn can be expressed in this manner, and that will be very helpful for us to study later on in the formation of postulates. And this is the definition of pseudo-positive operator. Next, we have given a generalized notion of pseudo-trace. See, normally trace of operator is defined through orthonormal basis. But here, to study the pseudo-Hermitian Hamiltonian, we cannot use the orthonormal basis. Rather, we can use a pair of raised bases, and the formula is given by this. And this is the definition of trace preserving operator. Now, we have proposed few postulates for pseudo-Hermitian quantum mechanics. Although there are many debates in the recent research as far as the postulate of pseudo-Hermitian quantum mechanics is concerned, we also have proposed few postulates, and linear operator is pseudo-density operator if this P is pseudo-positive and partial stress is 1. Second, we proposed a pseudo-positive operator value measure using a different concept that is in the previous, when I discussed about POVM, we were using positive operator. But here we are using pseudo-positive operator. Although this resolution to the identity is the same. And the third, we also give another method of probability distribution by using this pseudo POVM, and the formula is given in this manner. Now, the time evolution operator which we proposed is like this. Let H be pseudo Hermitian, no need to be Hermitian, and we define B by this formula. And of course, if H is Hermitian, then this happens to be unitary. But if H is not Hermitian, if it is pseudo Hermitian, then it happens to be pseudo unitary operator. Now, coming to the next concept, that is quantum channels in pseudo Hermitian quantum information. Quantum channels are quite useful in modern sciences, like in digital sciences or signal processing, and even in quantum mechanics. Now, just let us recall what is a completely positive operator. See, the an operator from LH, space of all the bounded linear operator, to set of all the bounded linear operator on K is said to be completely positive if it satisfies these conditions. And recall again, what is quantum channel? Mathematically, quantum channel is represented by a linear operator from LH to LK, satisfying the two conditions. The first condition is this phi has to be completely positive and it has to be trace preserving. Now, since in pseudo Hermitian quantum information or in quantum mechanics, the notion of positive is pseudo positive, so therefore we need to modify the concept of complete positive by using pseudo completely positive operator. And this is the definition that we have proposed for a pseudo completely positive operator. And the second thing is, we propose that the pseudo quantum channel, and this operator is said to be pseudo quantum channel if it is pseudo completely positive and it is trace preserving in the sense of pseudo trace. And there are many representation to identify or to represent this quantum channel. Here we have given what is called cross representation of characterization of pseudo quantum channel. And let H and K be finite dimensional complex Hilbert spaces, and these two are metric operator here. This linear operator is said to be this linear operator is completely positive and pseudo trace preserving if and only if there exists a linear operator from LHK such that it satisfies this condition and the second condition. Similarly, there are other representation like equivalent conditions, like this is completely positive, and then if it is completely positive, then cross representation will fulfill this condition. And another one is Stiepner-Pring representation, and another one is choice representation. Now, here, the beauty of this representation is, this is an operator. This operator can be expressed with some decomposition, and in fact, this theta L are known operators. Like for example, when we look at the singular value decomposition, we decomposition a matrix into the product of unitary operator, diagonal operator, and you know that the unitary operator and diagonal operator are known to us. Similarly, in that fashion, we have decomposed this operator into the product of some known operators. And similarly, Such representation can be also correlated or characterized with Stirnitz-Prien representations, and also with some Choi operator. So these are the references. Thank you.
Okay. Thank you very much, Professor Coley Timothy. Are there some questions, observations, or two similar facts? Nothing? Okay. Bueno, thank you very much, Professor Timothy Pomay.
Thank you. Thank you.
We have time. Next talk is from Ruchika Verma, Professor.
Yes. Hello, everyone. Am I audible?
Okay.
Yeah. And my screen is visible?
Yes.
Yeah. Thank you, sir. Thank you for giving me an opportunity. And I really thank organizers for giving me opportunity to present my talk here on this platform. The topic of my presentation is a study of rationalized Toeplitz-Hankel operator. And if I start with the, I think there's some, yeah, this is the outline of my presentation. I'll be giving some brief introduction and history of Toeplitz and Hankel operators. And then which started in the early 20th century, and in 1911 it basically started by O. Toeplitz, and then fascinated by all these Toeplitz and Hankel operators. In 1995 the notion of slant Toeplitz operators were introduced by Professor Mark C. Ho. And then we introduced the notion of slant Hankel operators because the study of Toeplitz and Hankels, they go parallel, and therefore many generalizations of slant operators were discussed. And recently I have introduced the rationalized Toeplitz-Hankel operators, which is the rationalization of all such kind of operators. So this is just a brief history that I want to mention here, that the study of Toeplitz operator began almost in the beginning of 20th century by O. Toeplitz, and a lot of work has been done by different researchers around the globe. Together with the class of Toeplitz operators, the class of Hankel operators has been studied, and it is one of the most important class of operators on the Hardy spaces. Toeplitz in the year 1911, they studied infinite matrices. He related Toeplitz operators with the infinite matrices and with the northwest and southeast, diagonals constant. So basically the Toeplitz matrices, he has started with a study of matrices, and then with the help of matrices, he defined operators, and those operators were called Toeplitz operators. And they are very important in many applications, such as prediction theory, boundary value problems for analytic functions, singular integral equations, and they're also very useful for proving index theorems in the framework of non-commutative geometry. So as I mentioned earlier also, that motivated by the study of Toeplitz operator, Mark C. Ho in the year 1995 introduced this class of operators called the slant Toeplitz operators, and submitted his PhD thesis under the supervision of Professor Carl Cowan in Purdue University. And he has at that particular time, 1995 to 1997, he published 3 research papers where he discussed the algebraic properties as well as the spectral properties of slant operators. And inspired by this study, we introduced in the year 2002, I have introduced the notion of slant-Hankel operators, and further these notions also have been generalized to kth order slant operators and the slant-Hankel operators, and studied simultaneously by different mathematicians around the globe. And recently in 2021-22, a rationalization of all such kinds of operators is introduced and studied. So the basic terminologies that I'm going to use here, that the underlying space that we are going to consider is the space L2, which is a collection of all complex valued Lebesgue measurable functions on the unit circle, and that are square integrable. And then with the help of the inner product defined in this fashion, L2 is a Hilbert space, and with the orthonormal basis in a product, it is defined where G is nothing but the complex conjugate of G, and Zn, which is e to the power I n theta, is an orthonormal basis of L2. And for every function in L2, we define the Fourier expansion of L2 as sigma of an e to the power I n theta, and starts from minus infinity to infinity, where the coefficients an, they are the Fourier coefficients, and they are given by 1/2 pi I integral 0 to 2 pi f e I theta e to the power minus I n theta. And the Hardy space H2T is the set of all analytic functions, meaning thereby that if the Fourier coefficients, negative Fourier coefficients are 0, and the expansion, if I talk about the Fourier expansion from 0 to infinity, so that's the Hardy spaces. We also consider the function space L infinity, which is a collection of all essentially bounded complex valued measurable functions on the unit circle. And we can observe from here that if phi is any element of L in infinity and f is any element of L2, then phi f is always an element of L2. So with the help of this, a multiplication operator, and sometimes it is also called the Laurent operator, is introduced, and on the space L2, and with the induced symbol phi, which is in L infinity. So m phi of f is phi f for every f in L2, and this is well defined because, as I mentioned earlier also, that if phi is in L infinity and f is in L2, then phi f is always there in L2. And that's a trivial thing that we can prove it. So this is called the multiplication operator or the Laurent operator on the space L2. And the characterization is well known, and it is proved a few decades ago that as mz we have taken here to be the bilateral shift, and as the commutant of the bilateral shift is the set of all multiplications on L2. So it is proof that A is a multiplication operator if and only if it commutes with the bilateral shift. That is, if it satisfies this operator equation, mza equal to amz, then A is the multiplication operator or the Laurent operator. If we consider this matrix of this multiplication operator with respect to the orthonormal basis, and if we consider the Fourier expansion of phi as sigma ai zi, then we can observe from here that the matrix of this operator is nothing but a matrix where diagonals are constant. That is, if you see the main diagonal, that every diagonal parallel to the main diagonal, it's a constant. And the ijth element of the matrix is nothing but ai minus j, where ai is nothing but the Fourier expansion, ith Fourier coefficient of phi. So, and we can also observe that, as I mentioned earlier, that you can see the ijth entry is always equal to I plus 1th j plus 1th entry. So these all are constant diagonals parallel to the main diagonals. So as I mentioned, the Henkel operator, basically they are the operators which are which are defined with the help of multiplication operators and with the help of reflection operator on L2, where reflection operator is nothing but f of z is equal to z f z bar. So if I consider for phi in L infinity, the Henkel operator S phi on L2 is defined as S phi of f is j m phi of f, where j is the reflection operator on L2. And we can observe here that again, if I consider the matrix of this thing, slant Henkel operator, it is nothing but ai minus j, which is, that means the characterization that we have for it is for Henkel operator is that any operator will satisfy this equation, operator equation mz bar a equal to an. So it is not commuting with mz, the bilateral shift, but we can see here that mz bar a is equal to amz. Then we say a is a, so it is both ways. It is a characterization of a Henkel operator with the help of bilateral shift. And we can see that the Henkel is nothing but the reflection of multiplication operator, and because j is the flip operator, it is taking fz to fz bar. Then Toplitz's operators, they are nothing but the compression of Toplitz's operators. They are the compression of multiplication operator or the Laurent operator on the space H2. And we define, since we have taken the underlined set as a circle, we can define Toplitz's on the notion of Toplitz's operators and Henkel operators. They're defined on different spaces like the disk and the Bergman spaces on the torus also. So here I'll be dealing with the unit circle with the standard Lebesgue measure defined on it, and L2 is the Hilbert space, again of square integrable function. Then for phi in L infinity, the operator T defines a multiplication operator on L2, and let P be the projection from L2. So compression of the multiplication operator from on H2, the Hardy space is a Toplitz's operator. And if we see, because it is a compression only, so the right hand quarter of the matrix of multiplication operator is nothing but the matrix of the Toplitz's operator. And the bounded linear operator on H2 is a Toplitz's operator if and only if the matrix representation is given by this. So it is nothing but the right hand quarter of the multiplication operator and the matrix of the multiplication operator. And it has the same behavior that it is constant along the diagonals. So in the past, for several years, slant Toplitz's operators have played outstanding roles in wavelet analysis, curve and surface modeling, and dynamical systems. For example, Williams has associated the Bessev regularity of solution of the refinement equation with the spectral radius of an associated slant Toplitz's operators, and has used the spectral radius of the slant Toplitz's operators to characterize the LP regularity of refinement functions. Also, Goodman and other mathematicians, they have shown the connection between the spectral radii and the conditions for the solution of certain differential equations that in the Lipstick's classes. So, however, these mathematicians concentrated mainly on the applications, but these considerations serve as a source of motivation to introduce and study the properties of slant Toplitz's operators. In 1995, Ho began the systematic study of slant Toplitz's operators on the Hardy spaces. And for initially, he, as I mentioned earlier also, that he introduced, he published 3-4 research papers, in which the first paper was the algebraic property of slant Henkel operators. And then he has also published one paper on the compression of slant Henkel operators on the space H2, and he has discussed various properties of that. So we in the year 2002 have introduced the notion of kth order slant Toplitz's operator, but for k greater than or equal to 2, and discuss some properties of kth order slant Toplitz's operators, which is a generalization. Even some authors have defined slant Toplitz's operators and their generalizations on different spaces and studied some properties of these operators. So this is the first systematic study that Mark Seho defined, that the slant Toplitz's operator with the help of another operator W on L2, which takes even if W of Z2n, Zn's, they are the basis elements of L2. So he has defined the operator with the help of basis elements such that it takes odd to 0 and evens to half of them. And so he has defined the operator A5 from L2 to L2 as A5F is WM5 of F, where M5 is nothing but the multiplication operator. So he has defined the definition that he has given. It is nothing but A5F is equal to WM5. And then he proved the characterization that any bounded linear operator on L2 is a slant Toplitz's operator if and only if it satisfies this operator equation MZA equal to AMZ square. And that is, we can write A as WM5. And you can see here that if we consider the matrix of slant Toplitz's operators, it is not diagonals. They are there are two observations in this matrix. It is nothing but the diagonals having the increasing Fourier coefficients. If you see the main diagonal, the first is the A0, A1, A2, A3, and so on. And you can see each diagonal, they are in increasing order of the Fourier coefficients. And also the second observation is that they are making the loops of this kind also, that A0, A minus 1 that I have marked with the red color. And there is one also observation that why they have given the slant name, that is maybe if you rotate the matrix of Toplitz's operators or the multiplication operator through an angle of 45 degrees, you will get the matrix of slant Toplitz's operators. So likewise, we in the year 2006 introduced with S.C. Arora, myself, R. Batra, and M.P. Singh, we have introduced slant Hankel operators, and which is a flip of nothing but the reflection operator. With the help of reflection operator, we have defined the slant Hankel operators. And we have given the characterization with the help of this thing. Then this is the generalization of slant Toplitz's operators, and which is defined as that we define for all k greater than equal to 2, Wk Zn is equal to Zn by k if n is divisible by k or 0 otherwise. And we have proved that A is a kth order slant Toplitz's operator if and only if it satisfies the operator equation MZA equal to AMZK. And some properties of generalized slant Toplitz's operators and yeah.
हाँ तो सकूंगा क्योंकि मैंने कोई काम को ना रात ना होगी मेरी प्रेजेंटेशन धक्के खाना समझ
So if I consider this operator, you can define also, since this was the first definition, introductory definition that we have given, that U phi f is equal to Wk M phi f for all f in L2. But then later on, we can also define with the help of basis elements as U phi of Zl is equal to sigma I varying from minus infinity to infinity, Aki minus Lzi. And there are some results, algebraic properties. We have also proved some spectral properties of this operator, like if phi and psi, they are the two symbols in L infinity, then the product of kth order slant Toplitz's operator is a slant Toplitz's operator. It is a if it is compact, if and only if this happens. And also we have studied the compression of U phi to H2. It says that the two results about the spectrum, we have got that the spectral radius of V phi equals to the spectral radius of U phi only when if phi is analytic or co-analytic. Co-analytic means that if phi bar is analytic, we say it is co-analytic. Where V phi is nothing but the compression of U phi to H2. And this is the one result that we have received, that we have got that if T phi is invertible, then the spectrum of V phi contains a closed disk, and the interior of the disk consists of eigenvalues of infinite multiplicities. Now, recently in 2021-22, we have introduced the new notion, which is the rationalization of all Toplitz's Hankel operators. And with the symbol phi in infinity, we define our phi f with from L2 to L2 as Fi f equal to Wk1 And we have defined K1 and K2 are two non-zero integers. And we defined the rationalized Toeplitz-Hankel operator of order K1 and K2. For f in infinity, where K1 and K2 are non-zero integers, M phi is a multiplication operator. And we have denoted this set as RTHO, the set of all rationalized Toeplitz-Hankel operator. And now here we have taken K to be a non-zero integer, and we define with the help of basis WK from L2 to L2 as WK Zi is equal to Zi by K if I is divisible by K and 0 otherwise. And this blue one, I have marked that this is the main result, that which gives me the characterization, because they are the two non-zero integers. So we have proved this characterization of a bounded linear operator to be a rationalized Toeplitz-Hankel operator of order K1 and K2 if it satisfies this operator equation. And we have given the proof in two parts. Firstly, for the relatively prime integers K1 and K2. And then if they are not relatively prime, they have a common divisor, then we have defined in that way also. And for proving this main theorem, we have also proved these results, which we treated this as lemma, because we are defining the rationalized Toeplitz-Hankel operator with the help of WK. So we need some properties of WK. And it says that the very first is the norm of WK is 1. And if WK star is the adjoint of WK, then WK star Zi is equal to ZKI. And it will not commute with MZ, the bilateral shift, but the behavior of WK is that MZWK is WK MZK. And these are few results that we have got for WK, and with the help of these 6 results, we have got this our main result that says that a bounded linear, firstly, as I mentioned earlier also, that we have proved this for the relatively prime integers, that for a given relatively prime integers K1 and K2, if any bounded linear operator on L2 satisfy this operator equation, then it is nothing but a rationalized Toeplitz-Hankel operator, and conversely also. So the necessary part is very trivial, because if I assume that the way we have defined the rationalized Toeplitz operator, and we consider that let R equal to WK1 M phi WK2 star, then we can see that R satisfy this operator equation MZK2 R equal to R MZK1. But for the converse part, we have constructed phi, and then we have proved that if any bounded linear operator which satisfying this, then it must be this. So firstly, we defined, we have decomposed like this, R of ZFK with the help of basis elements we have defined. Then we have taken phi naught to be R1, where R1 is this one, R of Z naught. Okay, and then RZ square, ZK1 minus 1. So we have proved in the, I have not given the entire proof because it's a very long proof. And we have proved that all these are bounded. And with the help of this, we have defined phi naught as R1, phi 1 as RZ. And in this way, we have defined a function phi z, and we have proved that this function phi z is nothing but an element of L infinity. And therefore, f in L2 can be written in this form. And then with the help of that phi z and those properties that we have proved for WK, we have started with WK1 M phi WK2 star of f. And we have proved that because of all the properties of WK that we have proved in that lemma, that it is nothing but RF. So therefore, R would satisfy this equation, where I started with this when K1 and K2 are positive integers. But if they are negative integers also, then we can have some calculation, and we can say that this is the equation would be satisfied, and hence we have this thing. But however, as the previous theorem, as I told earlier also, that we have proved the 2 theorems for the characterization. Firstly, for the relatively prime integers. And secondly, what happens if K1 and K2, they are not relatively prime? So in this case, if we K1 and K2 have the greatest common divisor D, and if we can write K1 as Dn and K2 as Dm, and the closed linear span we have taken, and we split your L2 space with this N naught plus a direct sum N1 and so on. And we can define now for any non-zero integers K1 and K2, this R is satisfy this operator equation if and only if with respect to this. So this is the way we have split L2 into those closed spaces. And therefore, I can say that R5 is a rationalization of all Toeplitz-Hankel operators because of the following. Because if I take K1, K2 is 1, it becomes a multiplication operator and Hankel, and therefore slant Toeplitz, slant Hankel. And so it is the generalization of all. So this is the main thing that we have got, that any boundary linear operator on L2 is a rationalized Toeplitz-Hankel operator if and only if satisfy this operator equation. And therefore, with the help of basis elements, if phi is equal to sigma ai zi is the Fourier expansion of phi, then we say of order K1 and K2 if R phi of zi is equal to this summation of this thing. So with the help of Fourier expansion of phi, we can also define R phi. So this we can treat as a definition again. And but interestingly, what we have found here, that the adjoint of this operator may not be a rationalized Toeplitz-Hankel operator. So it is not satisfying this thing. And as there is a theory of Toeplitz with its matrix, Hankel with its matrix, Land Toeplitz with its Hankel. So we have also defined the notion of rationalized Toeplitz-Hankel matrix of order K1 and K2. And what we have achieved, that it is a matrix with satisfying that ijth element is always equal to I plus K2 and j plus K1 element. And therefore, the structure of the matrix is this, and the ijth element is given by ak1i minus ak2j. And you can see here that if you substitute some particular values of k1 and k2, you'll get the matrices of Toeplitz and Hankel from it. Some results I have mentioned here. That given a pair of non-zero integers, this is compact if and only if. That means there's no non-trivial compact operator. Also, there it's self-adjoint if and only if wk phi equal to wk phi bar. It is hyponormal if and only if mod of wk phi square is equal to w minus k phi square. And if m phi is a multiplication operator, then the product of the multiplication operator and the rationalized Toeplitz-Hankel operator is again a rationalized Toeplitz-Hankel operator, but that symbol is different. You can see here in the last line that m phi z, r psi z is nothing but this. And this is in general also, we have got that if K1 and K2 are non-zero integers such that different modulus, then K1 and K2 are relatively prime, and this is normal if and only if phi is 0. And if they are not relatively prime, this is normal if and only phi d of f. WD of phi is equal to 0, where D is the greatest common divisor of K1 and K2. So with this introduction of rationalized, so we have also introduced and studied the notion of weighted rationalized Toeplitz-Hankel operators on the weighted spaces and discussed some properties of these operators, and also the notion of essentially rationalized Toeplitz-Hankel operators on the space L2 is introduced, and some properties of the set of such kind of operators are discussed. Also, conditions under which the product of two such operators commute are also discussed. And we have denoted that by ERTHO on L2, the set of all essentially rationalized Toeplitz-Hankel operators. So these are some references that recent papers in where we have introduced. We have also done the essentially lambda rationalized, essentially weighted rationalized Toeplitz. And so these are few references that I have mentioned here. And in this seventh reference, we have introduced the notion of, in 2005, the notion of generalized length, which is published in NARWIT. So that's all. Thank you so much.
Thank you very much, Professor Ruchika Verma. Are there some questions? Nothing? Okay. Thank you very much again, Ruchita
Thank you,
Verma.
sir. Thank you, sir. Thank you so much.
Next talk is from Professor Arti. Professor Arti. Nikhil, do you know the Professor Arti? Oh, okay. Excuse me.
Am I audible, sir?
Okay. Come on.
Yeah. Hello, everyone. Myself, Aarti. I'm a PhD scholar from Department of Mathematics, University of Delhi. First of all, I would like to thank to all the organizers for giving me this opportunity. Today, what I'm going to present is titled as Fourier Analysis over Finite Heisenberg Group. This is the overview of my presentation. Sir, my camera is not working. Is it okay?
Yes, Arti, your slides are visible. Please go ahead.
Okay, thank you, sir. So I would like to start my presentation with the Heisenberg group. Okay, what is Heisenberg group? The Heisenberg group over the cyclic group Zn is the matrix groups of upper triangular matrices of 3 cross 3, where principal diagonal entries are taken to be 1 and x, y, z are from the cyclic group Zn. This matrix group forms a group under the operation given as this: xyz, uvw are operationed as x plus u, comma, y plus v, comma, z plus w plus xv. Heisenberg group has a special structure. Like, first of all, it is a non-abelian group. Here, the order of operation matters.
Arti, your voice is not audible. Can you please check the connection?
When combined
Still, your voice is not audible.
group
Can you please check your connection, internet connection?
See.
Mm-hmm. It um, hmm, I was on a Heisenberg group. How this is how this structure is important. Like in representation theory also, representation theory does. Representation theory studies how abstract algebraic structures such as groups are realized
Excuse
as
me,
linear.
Yes.
your slides are not visible. I mean, I
Yes.
think you need to share the slides again.
Okay, sir. Sorry, sir.
Yes,
Okay.
now they are visible. Yeah, thank you.
Yeah.
Please go ahead.
Yeah, thank you, sir. So what I was trying to convey, like Heisenberg group has its own importance in representation theory also. Like what representation theory does? Representation theory studies how abstract algebraic structures such as groups are realized as linear transformation on vector spaces. In representation theory, unitary representation are of particular interest because they preserve inner product and norms. Are of I'm sorry, sir, my connection is poor actually.
Yes. Do you can continue your talk, please?
Yeah, thank you, sir. So I would like to tell you that Heisenberg group is isomorphic to semi-direct product of Zn square and Zn. Here Zn square is the structure, group structure, all the elements are the form 0, B, W, and Zn, his elements are the form X, 0, 0, where X is coming from the cyclic group Zn. They are the abelian groups, and phi is the group action. Phi is the group action of Zn on Zn square given by this map. Phi x VW are mapped to VW plus V comma W plus XV, where all x are coming from the ring of integers. Now, as because this Heisenberg group is isomorphic to this semi-direct product, every element of the Heisenberg group can be written as 0 VW multiplied U00. Next, we have the dual of the Heisenberg group. What is dual? Dual is the set of all irreducible representation of the Heisenberg group. Here, pi t sp is denoting the irreducible representation of the Heisenberg group for fixed t, where t is lying between 0 to n minus 1 and SB is lying between 0 to GCD of t comma n minus 1. Now, this is the beauty of the irreducible representation of Heisenberg group, that they all are induced from the one-dimensional representation. Here chi st bar, here chi st is the character of Zn square, and EB is the character of the stabilizer of Zn chi st. And their tensor is a representation on A semi-direct product B chi SB. And if we induced it to Heisenberg group, then these are the induced irreducible representation of the Heisenberg group. Here this right hand side gives the entire list of irreducible representation of the matrix group, Heisenberg group, and the dimension of each representation is n by GCD t comma n. Here we have the matrix form of irreducible representation of Heisenberg group. For fixed t lying between 0 to n minus 1, SV lying between 0 to GCD of t comma n minus 1, the matrix form of the irreducible representation is given by this map. Like when n by GCD of t comma n divides u plus j minus I, then the entries, ijth entry of the matrix will be exponential 2 pi I by n SV plus t w minus IV plus b u plus j minus I. Otherwise, it will taken to be 0. From the above, we have that, like first of all, observe, since this representation, since it is a representation, therefore it's a homomorphism. Hence, pi t sp at any UVW can be written as this product of these two matrices, pi t sp 0 VW and pi t sp U00. And here pi t sp U00 is nothing but the, for any u, by using the property of the homomorphism, this can be written as the power of this matrix. Pi t sp U00 is the power of uth power of this matrix. And this pi t sp 0 VW, this coming out to be simply a diagonal matrix.
Nikhil.
Yes, Professor Xavier. I'm just checking with Darti, and maybe
See.
some internet connection is problem with the internet connection.
See,
Yeah.
I don't see here.
No, maybe she will sign in again. Let me just check with her. I'll just get back to you. Thank you.
Hello, sir.
Yes, Aarti. Your screen is visible and everyone is able to see your slides. I think you can please go ahead. Please proceed.
So what we can express pi tsp UVW as pi tsp 0VW pi tsp U00. And so what we said ki this representation pi tsp U0 is difficult to calculate for the computer. Like if we increase the number U, then for highest power of U, this is difficult to calculate. So in this presentation, what I will give is the easy form of this matrix so that it is easy to calculate for the computer and it can help it further. So first I introduce diagonal matrix. QU for every U we have this diagonal matrix of order n by G2 cross n by GT. So how I defined it, whenever U is divided by n by GT, then our matrix is nothing but a constant diagonal matrix whose entries are alpha power n, where alpha is exponential 2 pi I b by GT. And if U is some L n by GT plus R, then Q is this matrix. Whenever I is varying from 0 to, then is ith entry. Whenever I varying from 0 to R minus 1, this is alpha power L plus 1. Whenever I varying from R to n by GT minus 1, then it is alpha power L. So here we have this configuration that how we can express with the help of this matrix pi tsp U00 as the T minus U QU, where T is the translation matrix and Q is this diagonal matrix. So now by the multiplication of this matrix, we can easily calculate that matrix. Next, we have the main result of this. So as we see, pi tsp UVW can be expressed by pi tsp 0VW and pi tsp U00. So, and pi tsp U00 nothing but the T minus UQU. So we can express our irreducible representation for any T lying between 0 to n minus 1 and SB lying between 0 to GCD of T comma n minus 1 to be the product of these unitary matrices, where S is the multiplication matrix, M is the modulation, T is the translation, and Q is the diagonal matrix. In particular, for n equal to P, our Q is coming out to be identity matrix. So we have this form, and S is equal to 0. So this can be expressed as STW M minus TV T minus Q, where S is the multiplication matrix, M is the modulation, T is the translation. Next, we give the Fourier transform over Heisenberg group. Before that, we define a few maps. Like first map, we define F naught SP from the Hilbert space L square H3Zn to the set of complex number, such that for each element F is mapping to the inner product of F ka inner product with pi 0 SP. Second, we define a map. Furthermore, we define another map F naught from the Hilbert space L square H3Zn to L square Zn tensor L square Zn, such that each element F from the Hilbert space L square H3Zn is going to E bar 0s tensor, E bar 0b tensor, F naught SPF, where what is E0s? The standard orthonormal basis for the Hilbert space L square H3Zn. Next, we define maps for like when T is not equal to 0. Here, E bar Tj is taken to be standard orthonormal basis for L square ZGT, where GT is the GCD of T comma n. And we define a map FTSP, a mapping from the Hilbert space L square H3Zn to M tau TC, such that for every element F in the Hilbert space is mapping to the F inner product pi t sp. Furthermore, we define another map ft from the Hilbert space L square S3Zn to L square Z gt tensor L square Z gt tensor m tau t c. Here, FTS is the summation sp0 to gt minus 1 ETS tensor ETB tensor FTSP F. As they all are the matrices. FT is a matrix. FTS, they all are well-known matrices. From here we can say. So now we're defining a Fourier transform over the Fourier transform over S3Zn is a map from the Hilbert space L square S3Zn to this. This is not a direct, just a notation where H naught is L square Zn tensor L square Zn and Ht is L square Zgt tensor L square Zgt tensor m tau t c for all t varying from 1 to n minus 1. So here we have given the Fourier transform for the Heisenberg group. Next we have the adjoint of this map. These are my references. Thank you.
Thank you very much, Professor Arti.
Thank you, sir.
Some questions? Any questions? No? Okay. Thank you very much, Professor Arti. Thank you.
Thank you. Thank you, sir.
Arti, can you please stop sharing your screen now?
Yes, sir. Sorry, sir. I forgot.
Okay. Thank you very much. Carol, do you
Hi,
want
Professor
to continue?
Javier. Yes, I can continue. Thanks, many thanks. Professor Sharma, is Professor Sharma here? I think so. So let's start the second part of the lectures today, of the second day of this conference. The next speaker is Professor Haksha Sharma. Are you here? Are you ready? Should we start?
Good morning, ma'am. Yes, I'm here. I'm ready, ma'am.
Oh, that's nice. Could you share your screen, please?
Yes, sure.
Welcome. So, the next
it
speaker. Okay.
Is it visible? Is the screen visible?
Oh, yes, it's visible. It's bright. Thanks. The next speaker is Professor Raksha Sharma, and the title of her talk is 9-mark type results using frames. So, Professor, the word is yours. Go ahead.
Thank you, ma'am. So, good morning, everyone. So, I will be talking about 9-mark type results using frames. So, in this talk, my talk consists of introduction, frames, and Rees basis, frames associated with sequence of scalars, quantum measurements, and finally, we will be discussing the error in the probability. So, starting with the frames, frames are actually used as tools in signal processing, image processing, data compression, sampling theory. Frames are also used to mitigate the effect of losses in packet-based communication system to improve the robustness of data transmission. In such cases, Kazasa and Kutnioki observed that data assigned to one single frame system becomes too large to be handled numerically. So it will be beneficial to split large frame systems into smaller systems and then process the data locally. It is therefore, there was a requirement of a distributed frame theory, or we can say the set of local frame system. So in this direction, Kasasa and Kutnioki and Lee developed a framework to deal with such types of application, and they introduced the frames of subspaces or called fusion frames. There is to describe and analyze the behavior of quantum systems, mathematical frameworks is used, and it is a very powerful way to represent quantum mechanical fundamental quantities. So in this direction, Adler and Forney studied the relationship between rank 1 quantum measurements and tight frames. They also defined the frame matrices in analogy to the measurements of measurement matrices in quantum mechanics. Further, Newmark theorem extended to tight frames to orthonormal basis. Though the motivation of least square measurements of quantum mechanics, they constructed optimal tight frames. Now, in this talk, I will give some Newmark type results, and I will also state a formula to give average probability of an incorrect measurement using false. Coming to the standard definition, the sequence Xn in Hilbert space H is said to be frame for H if there exist constants A and V, which satisfies the equation 1. The equation 1 is A norm of X square is less than equal to summation of inner product X Xn mod square less than equal to B norm of X square. The positive constants A and B are called frame bounds. And if A is equal to B, then the frame is called a tight frame. And if removal of even one Xn renders the collection of Xn no longer a frame of H, then that frame is called an exact frame. For example, the orthonormal basis for H is both a tight and exact frame for H. In the inequality 1, the left half inequality represents that the frames are complete. Coming to the frame sequence, a sequence Xn in H is called a frame sequence for H if Xn is also a frame for linear bounded space Xn. However, a Bessel sequence in a sequence Xn in Hilbert space H is called Bessel sequence if there exists a constant B, a positive constant B, such that mod of inner product such that xn inner product mod square is less than equal to b norm of x square. This is actually the upper inequality of the equation 1. The equation 1, the upper inequality represents the Bessel sequence. Now the Rie's spaces. The Rie's space is a sequence of the form UN, where En is an orthonormal basis for H and U is from H to H, is a bounded bijective operator, is called Rie's basis for H. If Yn is equal to UN is a Rie's basis for H, then there exists a uniqueness sequence Zn in H such that X is equal to inner product xzn yn for all x belonging to H. Then the sequence Zn is also called a Rie's basis for H and is called dual Rie's basis for H. If Xn is a Rie's basis for H, then Xn is a frame for H. The converse need not be true. For example, any non-exact frame. If Xn is a Rie's basis for H, then for each x belonging to H, there exists a unique sequence of scalars alpha n such that x is equal to summation alpha n xn and summation alpha n mod square is less than infinity. This shows the convergence. This confirms the convergence. For a sequence Xn in H, the following statements are equivalent. That is, Xn is a Rie's basis. Xn is complete. There exist positive constants A and B, which satisfies your equation number 2. So the definition of the Rie's basic sequence is the sequence Xn in H is called Rie's basic sequence if Xn is the Rie's basis for complete linear span of Xn. The right half equality of equation number 2 confirms the Rie's Bessel sequence for H. The sequence in H is said to be Rie's basic sequence. Rie's Bessel basic sequence if it is a Rie's Bessel sequence of complete linear span of Xn. Now coming to the frames associated with the sequence of scalars. Then there is a let n is a union of Pn, where if there is a misprint, instead of Mi, there should be Pi, where Pi are finite subsets of n with Pi union Pi intersection Pj is phi, that is Pi's are disjoint. If mu(n) is any sequence of scalars, a sequence Xn in Hilbert space H is called a frame associated with sequence of scalars mu(n) if there exist the constants Al and Au such that Al norm of x square is less than equal to summation over inner product be less than equal to Au norm of x square. And the same condition, if Al is equal to Au, then Xn is called a tight frame associated with a sequence of scalars. And if Al is equal to Au, both equal to 1, then Xn is called a Parseval frame associated with sequence of scalars mu(n). Now by definition, Pn is a sequence of subset of n as defined in definition 2.1, and for orthonormal basis En of L2, let us consider L2 over Pn to be equal to summation of alpha j Ej, where alpha j are scalars, and summation of direct sum L2 Pn over L2 is equal to Un, where Un belongs to L2 Pn with a convergence condition. Notice that for n belonging to capital N, L2 Pn are subspaces of L2 and inner product defined on summation direct sum L2 Pn over L2 is given by inner product Un Vn summation inner product of summation over n varying from 1 to infinity Un Vn, where Un Vn belongs to the direct sum L2 Pn over L2 space. So summation n belonging summation n direct sum L2 P and L2 is a Hilbert space. So one can easily verify that the operator TB is equal to direct sum L2 Pn over L2 to H is given by TB summation alpha I ei n varying from 1 to infinity is equal to alpha I nu I xi. This is called bounded and is called synthesis operator of frame Xn associated with sequence of scalars mu n. Also, the bounded operator TB adjoint TB star from H to summation direct sum L2 Pn over L2 is given by TB star equal to inner product X nu I xi ai, and this is called analysis operator of frame associated with sequence of scalars nu n. Now by composing the operators TB and TB star, we obtain frame operator SB, where SB is defined as TB star from H to H. So SB is inner product of X mu I xi, which is equal to mod of mu I square inner product X xi over xi. Now xi SBX is, let Xn be a frame associated with sequence of scalars mu n. Let TB star be synthesis analysis operator, and SB is the frame operator of frame Xn. Now one may promptly observe that SB inverse SB is IH and SB inverse TB star, because SB is equal to TB star. Therefore, TB star is TB star SB inverse TB star, and hence SB inverse TB is pseudo inverse of TB star because it is satisfying above property. So TB star SB inverse TB is projection from summation direct sum L2 Pn L2 over TB star H. Now, if Xn is Parseval frame for H with respect to Pn nu n, then TB star is equal to IH, that is TB star is isometry. So in the following result, we have shown that Parseval frame associated with sequence of scalars for H with respect to Pn nu n is a compression of an orthonormal frame Yn associated with sequence of scalars for K with respect to Pn nu n, where the Hilbert space H is a subspace of Hilbert space K. Now coming to the theorem, let Xn be a Parseval frame associated with a sequence of scalars for H with respect to Pn nu n. Then there exists a Hilbert space K with H as a subspace of K and orthonormal frame Yn associated with a sequence of scalar for K with respect to Pn nu n such that Phin is equal to Xn for all belonging to n, where Ph is projection from K to H. Now coming to the quantum measurements, the projection valued measure PVM. A PVM on Hilbert space H is any set of operators En on H which satisfies the following. That is, each operator En is a self-adjoint projection for all n. Ei Ej is equal to 0 if I is not equal to j, that is they are orthogonal. And summation n En is equal to IH. So it was observed that POVM are more suitable than spectral measures in representing quantum observables. POVM, that is positive operator value measures on Hilbert space H, is any set of operators En on H which satisfies the following. That is, each operator En has to be positive and the summation En is equal to IH. Now, we will prove that Parseval frame associated with sequence of scalar for H with respect to Pn nu n can represent POVM. Let Xn be a Parseval frame associated with sequence of scalars for H with respect to Pn nu n. Then En is a POVM on H. Let pi be a POVM on Hilbert space H, then there exist disjoint partitions Pn of n with Pn is finite for all n and sequence of scalars nu n and sequence xn in H such that xn is a Parseval frame associated with sequence of scalars for H with respect to Pn nu n. We shall now present NAMAC type results using frames associated with sequence of scalars. More precisely, an orthonormal frame associated with sequence of scalars represents projection value measures in Hilbert spaces. This can be shown by a theorem. Let Xn be an orthonormal frame associated with sequence of scalars for H with respect to Pn nu n. Also, let En is equal to summation x nu I xi in a product nu I xi for n belonging to n, then En is a projection value measure on H. Next, we show that Parseval frame associated with sequence of scalar can also give a PVM through dilation theorem. Let Xn be a frame associated with a sequence of scalars for H with respect to Pn nu n. Then there exists a Hilbert space K with H as subspace of K, where Yn belongs to K with PH Yn equal to Xn for all n, and sequence of operators Fn on K such that Fn is a projection value measure on K, where PH is projection from K onto H, and Fn is inner product of Y, mu I, yi, mu I, yi for all for y belonging to K. Now, finally, concluding to the presentation, in the final conclusion, I am giving the formula for average probability of an incorrect measurement by using a frame associated with sequence of scalars, which we have studied till now. Now, let xi I be a unit normal state in Hilbert space H, and Pi, rho I, is the corresponding probabilities. That sums to 1. That is, the total probability is 1. And Xn be the Parseval frame associated with sequence of scalars for H with respect to projections Pn mu n. Then the average probability of an incorrect measurement is given by 1 minus summation rho I summation over xi inner product of xi nu I k nu k xk mod square, and the summation is for all the k belonging to Pi, and summation over I is over the entire range, that is from 1 to infinity. The results of these papers these are my references, and the results of these papers are under process. They have to appear in Journal of Function Spaces. Thank you.
Oh, thank you, Professor Sharma, for your lecture. Are there any questions? Any questions?
Yes, I have a question. I have actually two questions.
Okay, go ahead.
First is, in the beginning, Dr. Sharma mentioned about the work of Kasaja. So is there any motivation for that work?
Yes, sir. The technological advances significantly increase the demand of distributed processing. But frames are, however, too restricted for such applications. Therefore, it was necessary to go beyond the classical frame theory, and fusion frames, actually called the frame of subspaces, satisfy these needs.
So you mean if we need applications in different fields, or if the data is too large, then you need to modify the definition of a frame.
Yes.
Right. So
Yes,
same
sir.
way
Yes.
so for your work also, you have considered a modified version of frame, that is frames associated with scalars.
Yes.
So can you tell where it is advantageous in your work?
Yes, sir. Yes, sir. Sir, for our application in POVM, you can see, for example, in theorem 3, this modified version is suitable for defining ENs, is required for POVM, and the same argument is valid for PVM also. If you look at our formula, our last slide, for calculating average probability for an incorrect measurement, then you may note that this modified version has a role to play, that is the scalars are involved in that formula. That is why a modified version of the frames is used, not the standard frame. Thank you, sir.
So,
Thank
are
you.
there more questions? If no, I will ask the audience to open your microphones, and let's thank again Professor Sharma for your nice lecture. So let's
Thank
go.
you, ma'am. Thank you.
Thanks.
Thank you.
Many thanks. So, Professor Sharma, you can
Yes.
stop at sharing
Yes.
your screen, please.
Yes. Yes.
So the next speaker is Professor Ataullah. Are you here? Are you ready? Should we start?
Yes.
Oh, nice, nice. Could you share your screen and the slides, please?
I shall.
Yes, it's possible to see. Nice. So let's start. The next speaker is Professor Atollah Askari Hamed, and the title of his lecture is on S-elementary wavelets in R and their applications in solving integral equations. So, Professor Askari, the word is yours. Go ahead, please. Professor Askari?
There.
Okay, you can start, please.
Yes. Let's go. First of all, I would like to thank and appreciate Professor Hana and Professor Kaushik, as well as the organizers of this conference, for giving me this opportunity to present my work. Another problem is that because of time limiting, I will present my work more fast than usual. Excuse me before starting. This work is a common work with my student MJ Kherde and my colleague Dr. Saidi in Kerman University. And now I'm at Concordia University. Meanwhile, my in Concordia University, I'm working on this project. Doesn't work. This is the content of this talk. The word wavelet was first introduced by Haar in 1909, and it was developed by Choi, Doveshi, Dai, Liu, Mayer, Fang, and others. A special type of wavelet that is called S-elementary wavelet, first introduced by Dai and Larson and Spiegel. In this work, first I will introduce special cases of S-elementary wavelets, and then I will present a few examples for using this wavelets basis to compute the solution of integral equations, partial and partial differential equations. As I said, due to the time limit, and since in the started both parts of how to make wavelet sets and also their applications, is that the material will be present more quickly to get to the end. Here is the definition of an MRA in general, a multi-resolution analysis that will be denoted by MAR associated with a dilation matrix A. This matrix A is expansive. That means all eigenvalues have modulo greater than 1, and this closed subspaces Vj of L2 of Rn satisfy these 5 conditions. The most important part of this definition is the condition 5th. The scaling function phi is very important. In fact, everything is dependent on this phi to generate a wavelet associated to an MRA. It's very important. It's routine, and I guess almost all of audience are familiar with this definition. In case n equal to 1 in L2 of R, we recall an important theorem that we need several times. Let SI be a wavelet associated to an MRA, and phi is scaling function. Then we have these two results. The family of functions, the set of Z translations of phi is orthonormal if and only if the summation is equal to 1 in the frequency domain. It's equal to 1 almost everywhere Kc in R. Also, the second equality we need several times. The square of absolute value of Fourier transform of phi at Kc is equal to this summation in terms of the Fourier transform of the wavelet psi. This 2 power j is very important scaling. It's very important, and we will use it. We are going to introduce a class of S elementary wavelet as the basis function, and using them to present an operational computational method for solving nonlinear Fredholm equation and nonlinear Wörth integral equation. Few examples are presented at appendix. If we have time, I can use them. To presenting the methods, operational matrices for the S elementary wavelets are derived. The S elementary wavelet spaces along with these operational matrices are applied to solving integral equations. Here is the main definition 3. The measurable subset W in Rn, which finite measure is a wavelet set for L2 of Rn if the inverse Fourier transform of psi hat is equal to the characteristic function of W and W, B, an orthonormal wavelet for L2 of Rn. It's the general case. Following Dye and Larson, we call this type of wavelets as S elementary wavelets. The prefix S is for set. The following theorem characterizes a set is a wavelet set or not. Hernandez and Weirs proved this theorem. Let A be an expansive matrix, and let E be a subset of Rn be a measurable set, then E is wavelet set if and only if E is both an A dilation generator of a partition modulus null sets of Rn and 2 pi translation Zn translation generator of a partition modulo null sets of Rn. These two definition and theorem are very important. We will use this theorem, part 2 in particular, and this theorem in next few minutes. Here we give an example in R1 that shows the wavelets generated by wavelet sets are another category of wavelets different from the wavelets generated by an MRA. A wavelet generated by an MRA satisfies in part 2 and also in part 1 of theorem 2. And a wavelet set and its wavelet is associated to theorem 4, please. Hernandez and Weirs. This example, if psi is defined by psi hat equal to the characteristic function of Q, where Q is the union of these 3 intervals. These 3 intervals. As you can see, it's 4 intervals. As you can see, these 4 intervals are symmetric altogether, are symmetric with respect to origin. A simple calculation shows that all translation, 2 pi translation for L in Z is a partition of R. And also all 2j times Q for J in Z is also a partition of R. So by theorem 4, Q is a wavelet set. We will show that the corresponding wavelet is not associated with any MRA. If this wavelet be associated to an MRA, it must satisfy the theorem 2, part 1 and part 2. Here, if there exists an MRA associated to this wavelet, by theorem 2, excuse me, its scaling function satisfies this condition. The absolute value of Fourier transform of phi is less than or is equal to 1 if equal to 1 if the absolute value of the modulo of Kc is greater than 0 and less than 4 pi over 7, or these intervals. I gave a proof for this in Appendix B. If we have time, we can show it. And otherwise, we had equals to 0. But if we set J equal to the interval, open interval 0 and 2 pi over 7, then for any Kc in J, we have the absolute value of Fourier transform of phi is equal to 1, and also Fourier transform of Kc plus 2 pi is equal to 1. So we have this summation have only 2 terms and equal to 1, altogether 2 for all Kc in J. Since this J is not null set, its measure is Lebesgue measure is 2 pi over 7. So it's a contradiction with theorem 2, and this wavelet is S elementary wavelet, not a wavelet generated by an MRA. Another example, for a fixed G in R plus, let A transpose equal to B equal to this matrix 0 minus G or 1/2, G power minus 1/2 and 0, and let Q1 be this set. The union of yi and minus yi. I from 0 to infinity. For y0, we have this 4 points, convex hull of these 4 points, convex hull of these 4 points. And for other I greater than 1, while I is this set. Convex hull of these 4 points. Here is 4 points. Convex hull of these 4 points for every I greater than or equal 1. Q1 is this type. This figure is Q1 and its translations. The first one is Q1. This is Q1 and its translation horizontally. This Q1 and its translation horizontally, vertically, excuse me. The first one is horizontal, this is vertical. This is Q1 and its dilations, where Q1 is the first dilation. Its dilation for Z N or L in ZB negative. The spaces near origin will be covered by infinitely many sets. And finally, 0 will not be covered, only 0. The wavelet associated to this wavelet set is this type. Another two examples are will present in the appendix if we have time. The next example is for this WC, for C in the open interval 0 and 1. W index C is equal to union of these intervals, two intervals. For C equal to 0.5, we have this set. It's Shannon wavelet. It's Shannon wavelet. By theorem 2, part 2, the scaling function for characteristic function of WC is of the form Q of characteristic function of Q and C with this Q. And we had equal to this definition, we define Fourier transform of phi index C by this formula. It's according to theorem 2. Another quadratic that we have proved in reference 9 is if we define the Fourier transform of phi mk index C equal to this value times Fourier transform of phi hat translated by 2 in pi for k and m in z, and c in interval 0 and 1, where v hat index c is defined as in one previous formula. Then for a fixed k, the system of phi hat index mk for m in z is orthonormal basis for L2 of R. By definition 3, the inverse Fourier transform of characteristic function of WC is an orthonormal S elementary wavelet. We put psi hat by this formula. 3 intervals, not closed, not open. If we define this as usual for wavelets for psi hat of mk, for k and m in z, and c in interval, open interval 0 and 1, we showed that the system psi at index mk is an orthonormal basis for L2 of R. Here we prepared definition and show how to characterize the discretization of a function f. The function f is approximated by these two matrices, D and psi hat. D is defined by this formula here, and psi hat is this. With capital psi hat, here small psi hat, defined before. All of these functions are in L2 of 0 and 1. The support of all psi hat ik, the union of all of these psi and this ik is V, and it's so that V minus 0, 1 is almost null set. Its measure is smaller than every positive epsilon. Here, again, we show the construction of operational matrix of S elementary wavelets. If we use this inner product to computing P, K, index ij, P, K hat, index ij. And for A equal to I over 2 power K, the n plus 1 times n plus 1 matrix. Yes, matrix is this type. Okay. If we put capital V hat equal to this matrix, transpose of this matrix, then for every F, we have F is approximated by this matrix product. Phi is defined in 5, and H is defined here. H. This is H. HK is defined before. Phi hat IK is defined before. And finally, for A equal to pi over 2 power K, our matrix is this form. QK, Q hat K, index n plus 1. It's a upper triangular matrix with A over its diagonal and 2A the upper triangle. The details is not difficult, only relation 7 shows the definition of QC, because phi hat is known. We can compute it. And finally, these results and convergence analysis. That EB standard basis E0, E1, En transpose, E vector, and omega equal to this value. Then we have these relations, 8, 9, 10, and 11. All of these are depend on E, capital psi hat, and capital psi phi. And also the diagonal matrix omega times E. All of these are it's not very hard to compute these relations. And this is the convergence analysis if we take dk equal to this in a product of f and psi hat index c and k, and the summation of dik psi hat ik I from 0 to infinity is be the S elementary wavelet series of f in L2 of 0 and 1, then Fm by partial sum of this series converges to f in L2 norm as m tends to infinity. The experimental rate of convergence Rk, we use this formula. We use this formula and you will see the result in a table. Here is the first application of S elementary wavelets. Threshold integral equation of second kind. U of t equal to f of t plus integral from 0 to 1 k of s of t, s and t, sigma L from 0 to n fl times u over L is ds for n greater than 1, where f index L are functions in L2 of 0 and 1, and k of SOT, the kernel, is in L2 of 0, 1 cross 0, 1. These are given functions. U is unknown function, and n is a positive integer. This equation for n equal to 1 is linear and otherwise non-linear. In examples 9 and 10, we will use this. For similarity, we suppose that k of s and t is equal to k1 t times k2 of t. By equation 3, we get this formula 13. F, Fl, K1, K2, and U. We can approximate all this function by the product of these matrices. By substituting equation 13 into 12, and by equation 8, we have the following equation. This. So we have a matrix equation. The final result is this. By taking transpose on both sides of the above equation, we get the following equation. It's long but not difficult. Equation 14 is a system of nonlinear algebraic equation with unknown vector u. We solve this nonlinear system by the Newton method and obtain u as approximated by u transpose psi hat index mk. Example 9 is a special case. U is defined by U is equal to sine of pi t plus this 1/5 times this integral from 0 to 1 cosine of pi t times sine of ps times u power 3 s ds. The exact solution of this equation is this. In figure 1, part A and B, we gave the comparison between the approximate solution and exact solution. When we used P hat MK and psi hat MK. Table 1, absolute error comparison of the present method with the methods in other works. Here, the number 13 and 14 refers to the number of references that we will see in the end of this talk. Here, new method. Our method is reference 13 and then reference 14. Again, here it's for different values of C. C is belong to the open interval 0 and 1. The result of difference, for example, the first row here 10 over minus 3, the 10 over minus 5. And this is the graph of approximate and the function exact solution. Exact solution is blue. Again, it's another example. U of t plus this integral equal to e over t plus 1. The exact solution for this equation is u equal to e power t exponential. And the result is here. Here again, this 2, 1, and 13, these numbers refer to the number of references. As you can see, the results are good. And also the figure. Again, here the blue line is the exact solution. Here, we use that rate of convergence that we introduced for R from 8, 10, 12, 14, and 16. For values of x equal 0.1, 0.2, 0.3, 0.4, up to 0.9. The third example is the same. Because of time limiting, I will go ahead. And this is the graph of this function and this approximation. The fourth example. All all numerical computation is using wavelet sets, wavelet set basis. On this graph. Here is an example in two-dimensional again. This is Q2, similar to Q1, but in Q1, Q1 was the union of two sets that were similar. The first one was positive, another one was negative. Here we have the union of yi and union of y prime I from 0 to infinity. That y prime I and yi here, they are symmetric with respect to x-axis for I greater equal to y, 1. And y0 is the convex hull of these 4 points. And each yi is also the convex hull of these 4 points. 1, 2, 3, 4 points. But these points are not so simple and so accessible in the first glance. Q2 is this type, and this dilation. It's Q1, yeah, Q2 actually, is Q2. First dilation is blue. Yeah. Second dilation is black here. Fourth is green here. Again here, the origin will not be covered by these dilations. And this is the translation. All of XY space R2 will be covered by this translation and also by these dilations. So Q2 is a wavelet set, and its wavelet is this type. Another example is this. Y here, Y is this, the convex hull of these 4 points. Y0 all again the convex hull of these 4 points, and any of omega 0 is equal to this. For I greater than equal to 1, we have yi and wi, convex hull of these 4 points. Wi is here. Y prime I, Y. Y prime is defined in terms of yi. Y prime I is defined in terms of yi. Here again is Q3 and its dilation. It's first Q3. This is Q3. This is its first dilation. The blue is the first dilation. And then here. With other dilations, this space around the origin will be covered except zero, except origin.
Professor Ascari, sorry for interrupting you, but the time's finished.
Yes. Yes.
Sorry.
In a few minutes, I will finish.
Okay, great. Thank you.
The last example is this wavelet set and its associated wavelet. Here only it remained, you see, references. The main reference is Larson 3. And also 5, Dawishi, 7, Hernandez and 1, Hernandez and 8 also, Hernandez and Ruiz in particular, Hernandez and Ruiz. 9, my work and Ferde, it's ID. Also 10, Larson, and 11, Malat. The book related to Meyer is very important. Thank you.
Thank you, Professor Ascari, for your lecture. Are there any questions?
Yes.
Okay.
Yes, I have a comment for Professor Ascari Ahmed. First of all, Professor, thank you very much for accepting our invitation for this talk. I'm Dr. Nikhil, and we communicated over the emails. And as I remember, during the 2017 from Delhi University, Professor Kaushik invited you, but somehow there was some problem related to the traveling, and you were not able to attend the conference. So, it's very, pleasing for us to see you online. And the talk was really insightful and very interesting. We covered so many topics related to operational matrices, convergence analysis, approximated solutions of the integral equations. I'm very, out of curiosity, and since a lot of research scholars have joined this session, I just want to ask, is there any specific book on S-elementary wavelets so that that would be really helpful for the people who are going to study something related to wavelets and S-elementary wavelets? Yes, thank you.
Thank you. The main references is the book of Hernandez and Ruiz. Of course, they only present these, and nobody used and examined these wavelets for solving, to use them to solving integral equation and other computational works. We started, and it was very interesting for us that the result is very good. I don't know if your question is exactly this or not.
No, it's okay. We are just, from the point of view of a person who is just started reading related to wavelet, is there any specific book on S-elementary wavelets or any, the starting paper you can mention for S-elementary wavelets?
You mean I introduce a book?
Yeah. The initial papers on S-elementary wavelets.
No. I will publish. I have published a paper that is 980s. Yes.
Okay.
Last year, it's
Yeah.
using S elementary wavelets in Journal of Mahoney Mathematical Research Center, and also this paper, I hope to be able to publish this. I don't know, at least so far, I didn't see any book or paper related to these topics.
Okay.
Merci.
Thank you, Professor.
Thank
Merci.
you for your question. Are there more questions?
Oui. Yes, why not?
Oh, are there more questions? No?
Yes.
Why not? If no, let's thank, I ask the audience to open your microphones to thank Professor Ascari again for your nice lecture. Thank you, Professor. Thank you. Thank you very
Thank you.
much.
Thank you.
Thank you.
Bye.
Bye. Could you stop sharing your
Yeah.
slides, please?
Yes.
Thank you very much again, Professor. Very nice, thank you. The next speaker is Sushil Chandra Hawan. Are you here?
Yes, ma'am.
That's nice.
Hello.
Hello. Hello. Welcome.
Hello, everyone.
Could you share your slides, please?
Okay. Wait a minute. So, mhm. Mhm. Okay. It is-
Professor Chandra, is there an option to share your screen there
Okay. Wait.
or
So,
not? Could you put into a full screen? I think it would be better
Okay.
to us, please.
Mhm. It's visible, ma'am.
Oh, not yet. In the full screen, not yet. because I think it would be better to see.
Wait a minute, ma'am.
No problem.
Elections, gestures.
Maybe.
It is visible, ma'am.
Yes, it's visible, but I think it would be better to put in full screen. Unfortunately, it's too small yet to us, I mean.
See, it's still very small. I mean,
Yes.
as advised by Professor Maria.
my title, Numerical Solutions of Fredholm Integral and Fredholm Integral Differential Equations using Lysander wavelets. Now, abstracts is in this paper an operational matrix method based on their linear Lysander multi-wavelets has been proposed for solving Fredholm integral equations and Fredholm integral differential equations using Lysander multi-wavelets. Operational matrix of integration, the Fredholm integral equation and the integral differential equations are reduced to algebraic equations to test the contingency of the proposed methods. Some various examples have been solved, and the comparison of approximate the exact solution has been presented in graphically form. Further comparison of approximate the solutions obtained by proposed method with those obtained by Wilson wavelet method and the cosine and sine wavelet method has been presented in tabular form. Now, introduction. Wavelet and linear Lysander multi-wavelets stand at the forefront of contemporary signal processing, offering a transformative approach that transcends traditional methods in the inaccurate and the reliable signal analysis. Wavelet emerged as the versatile mathematical tools enabling the decomposition of signals into the various frequency components. In this paper, I'm sharing a method using linear Lysander multi-wavelets, operational matrix of integration 4 to 11 and 1418 has been proposed to find the approximate solution of Fredholm integral equations of second kind and the Fredholm integral differential equations. Now, linear Lysander multi-wavelets, I'm sharing the present in the scaling functions for linear Lysander multi-wavelets are defined as phi naught t equals to 1, phi 1 t equals to root 3 2t minus 1, and t is greater than equal to 0 and less than 1. Now, by the definition of multi-resolutions by analysis, the corresponding mother wavelets psi naught t and psi 1 t are given as psi naught t equals to minus root 3 4t minus 1 and 0 is less than equals to t less than 1 by 2, and here root 3 4t minus 3 1 by 2 is less than equals to t and less than 1. Further, by the translation of the relation of mother wavelets psi naught t and psi 1 t, the linear Lysander multi-wavelets are constructed as this. Now, for the m1 equals to 1, psi naught 0 t equals to minus root 3 4t minus 1, and t is greater than equal to 0 and less than 1 by 2, root 3 4t minus 3, and t is greater than equal to 1 by 2 and less than 1. Now, psi naught 1 comma 0 of t equals to minus root 6 8t minus 1 root 6 8t minus 3 and 0, and first minus root 6 8t minus 1 is the t is varying from 0 is less than equals to t and less than 1 by 4. Next, 1 by 4 is less than equals to t and less than 1 by 2, and for 0 1 by 2 is less than equals to t and less than 1. Now, psi naught 1 1 t equals to minus root 6 8t minus 5 for t is greater than equals to 1 by 2 is less than 3 by 4 root 6 8t minus 7, and t is varying from greater than equal to 3 by 4 and less than 1, and for 0 t is varying from greater than equal to 0 and less than 1 by 2. The scaling functions and the subfamily members are phi naught t, phi 1 t, and psi naught 0 t, and psi 1 0 function of t, and psi naught 1 comma 0 t, and further they constitute the linear Lysander multi-wavelets. Now, functions and approximations. The square integrable function u of x and defined on 0, 1 can be the expanded in terms of scaling functions phi I and the linear Legendre multivaluate psi of kn. There, the u of x equals to, and this and the 3.1, whereas the ci equals to u of x, phi of I x, and ckn equals to u of x and psi k cap kn of x. After truncating the infinite series equations, 3.1 takes the following form. Now, the u of x equals to 3.2, and whereas c equals to c naught, c1, c to the power 0, 0, c to the power 1, 0, 0, and up to so on. The last term is c1 m in comma 2m minus 1 transpose, and it's a 3.3. Now, and the psi of x equals to psi naught x, phi naught x and phi 1 x, psi naught to the power 0 and 0 x, and psi to the power 1, 0, 0 x, and up to so on. The last term is psi 1 m into 2 to the power m minus 1 of x transpose, and it's represented by the 3.4. Similarly, the two variables kernel of xt defined over the L2L and 0, 1 into 0, 1 can be approximated by using the linear Legendre multivaluates as follows. Kernel of x comma t is equals to this, and the where k kernel x equals to and ki, and last one say the ky is represented by the 3.5. Now, we will discuss about the operational matrix of integration. The integration of linear Legendre multivaluate psi of t can be obtained as integration 0 to t psi of t dt equals to p of psi of t. It's an 4.1. Now, where p is the operational matrix of integration of order 2 to the power m plus 2 into 2 to the power m plus 2 for m equals to 1. The operational matrix is given as, and the p equals to this, and is represented by 4.2. Solutions of Fredholm integral equations. Now, first of all, we consider the following Fredholm integral equations of the second kind. Now, u of x equals to function of x plus integration 0 to 1 kernel of xt u of t dt, and x varying from is greater than equal to 0 and t is less than equals to 1, and it's represented by 5.1. Using Legendre multivaluates for the approximations of u of x comma function of x and kernel of x comma t as u of x equals to transpose of c and psi of x, function of x equals to transpose of t and psi of x. Now kernel of x comma t equals to psi of transpose of psi of x and kernel of psi of t. Now, where the c is c and phi of x are defined in equation 3.3 and 3.4 by now using equations 5.2 to 5.4 in equation 5.1, where transpose of c psi of x equals to transpose of t psi of x plus integration 0 to 1 psi of transpose of psi of x and kernel of psi of t, transpose of psi of t, and c dt. C equals to I minus k minus 1d 5.5, and the approximation solution can be obtained from the equation 5.8 by the using of equation 3.4, 5.3, 5.4, and 5.5. Next, solutions of Fredholm integral differential equations. Now, first of all, consider the following FIT equations. U dash x equals to function of x plus u of x plus integration 0 to 1 kernel of xt ut dt, x varying from greater than equal to 0 and t is less than equals to 1, where the u of 0 is equal to u naught, and that's represented by 6.1, where the function of x and the kernel x comma t, where this known as u of x is the known functions to be determined. The function u dash x function of x kernel of x t and u naught are the approximated by the using linear Legendre multivaluates as u dash x equals to transpose of u dash and psi of x, function of x equals to transpose of x and psi of x, kernel xt equals to transpose of psi of x and kernel of psi of t, u naught equals to transpose of u naught and psi of x. By the integration of the equation 6.2, u of x equals to transpose of u dash p plus transpose of u naught into psi of x. By using 6.22 and 6.6 in equation 6.1, then will be the I minus k p transpose minus transpose of p into u dash equals to k u naught plus u naught plus x, and this is represented by 6.7. Here, we will discuss about some examples. Example first, consider the following Fredholm integral differential equations, and the reference is 19. And u dash x equals to 1 minus 4 by 3x plus u of x plus integration 0 to 1 x t u of t dt, and u not equals to 0. The exact solution is u of x equal to x 7.2, and by solution is, first of all, using the approximation from the unknown function u dash x, u of 0 and function of x, and kernel xt given the equation 6.2 to 6.6. Now, k equals to is represented by the 7.3 and transpose of x is represented by 7.4 and transpose of u dash is represented by 7.5. Now, the approximation solution u of x and the equation 7.1 is this, and is represented by 7.6. It is observed that the problem in this example of the approximate solutions are the same as exact solutions. Table 1 shows on the comparison of L2 errors in approximate solutions of the obtained by the linear Legendre multivaluates and the Wilson wavelet method, and it is observed that the numerical result for the m equals to 1 are much better than the result in the 19. Now, the following Fredholm integral equation 19, u of x equals to cos 4 pi x plus integration 0 to 1 t u of t dt, and x varying from is greater than or equal to 0 and t is less than 1. Now, the exact solution is u of x equals to cos 4 pi x, and solution is using the approximation of the unknown function u of x, function of x, and kernel xt is given the equations 5.2 to 5.4, and given is k equals to is represented by the 7.9, transpose of d equals to 7.10, and transpose of c is represented by the 7.11. Now, the approximate solutions of the equations is represented by the 7.7, and next is 7.12. Now, figure first is shows the exact approximate numerical solutions of equations 7.7 given by equations 7.8 and 7.12, while figure 1b depicts the absolute error. Table 2 shows then the comparison of L2 error in approximate solutions obtained by linear Legendre multiwavelets and case wavelets, and it's observed that the numerical results for the m equals to 1 are better than the results in 19. Now, here I'm presenting example 3. Consider the following Fredholm integral equation signs and the u of x equals to e to the power 2x plus 1 by 3 minus 1 upon 3 integration of 0 to 1 a to the power 2x minus 51 upon 9 u of t dt. and x varying from is greater than equal to 0 and t is less than 1. The exact solution is u of x equals to e to the power 2x and is represented by the 7.14 by the solutions is proceeding as in example 2 and using the approximation from the unknown functions is given as in equations 5.22, 5.4. Now the k equals to this and the transpose of d equals to 4.458, 2.417 and 0.607 and 0.100, 0.010 and say 0.0 and 0.005 and last is 0.000 and this is represented by the 7.6 and similarly now we can find the transpose of c is equal to this and it's represented by 7.17. The approximate solutions of these equations is 7.13 is as follows: u bar x equals to this and that is presented by 7.18. There are the figures of 2a and 2b. It shows the exact and approximate solutions, the absolute error respectively. Table 3 represent a comparison of L2 error in approximate solutions obtained by linear Legendre multiwavelets and Wilson wavelet. It is observed that the numerical results for m is equal to 1 are better than the result in 19. Table 3, L2 error in approximate solutions obtained by the linear wavelet, multiwavelets and the Wilson wavelet, 19th. Now the conclusion is an operational matrix of integration based on linear Legendre multiwavelets has been used for solving Fredholm integral and Fredholm integral differential equation. It is observed through numerical examples the accuracy for this method is better the case cosine and sine wavelet method and the Wilson method 19. These are some references of my present paper and the YLI and the E-Bablin's Savashan and the Boolean, and similarly these are Arora and Anas Chauhan and O Chitragupta, E Hamzan and the F Kellen S A Yusufi and S Paul like a VK Singh, L Z and Stan and the X Wing. Thank you. Thank you so much.
Thank you very much, Professor Sushu, for your talk. Are there any questions? Any questions?
No, ma'am. Thank you.
No. Let's thank again, Professor Sushu. Thank you very much and sorry the inconvenience. Thank you.
No. Thank you. Thank you.
Thank you. So the next speaker is Professor Lourdes Palacios. Are you here?
Yes, I'm here.
That's nice. Could you share your screen, please?
Yes, sure. Let me know if you can see it. I'm just going to adjust this.
Yes, I can see, but yes, it's better now. I can see perfectly. Thank you.
Okay.
So let's introduce. The next speaker is Professor Lourdes Palacios, and the title of her lecture is The Algebra CV0 of All Continuous Weighted Vector Valued Functions and an Overview. So, Professor Lourdes, the word is yours. Go ahead.
Thank you so much. Thank you so much. Well, first of all, I would like to thank the organizers for giving me the opportunity to be in this conference and deliver this talk. Well, as Professor Maria Carolina announced, the title of my talk is The Algebra CV0 of XA of All Continuous Weighted Vector Valued Functions And before I start giving my preliminaries, I would like just to emphasize that the idea of this work comes from the fact that we were dealing with topological algebras, especially locally M-convex or locally convex algebras, and we wondered what or which properties of A were inherited to the algebra CV0 of XA. So most of the things that I'm going to do I will point out how these things works. Algebras of continuous functions have been a very interesting topic in functional analysis, in particular in the field of topological algebras. And let me just give you the structure of my talk. I will give a little introduction. Then I will point out some preliminaries, concepts, notions that we will need. And then I will go especially to the properties of CV not of XA. And finally, I will talk a little bit about projective limits to end with the Arens-Michael decomposition, which is a very important tool in the study of non-norm topological algebras, especially locally convex algebras. So, in order to start with it, I will keep on with what I was saying. One of the main interests in the field of this subject in topological algebras, is their algebraic and topological structures. A particular case in this sense is the class of weighted algebras of continuous functions. These algebras of complex valued continuous functions defined on a completely regular Hausdorff space X, where a family V of upper semi-continuous functions acts as weights in the definition of these spaces. Some spaces of vector-valued continuous functions have also been extensively studied. The most relevant is C of XA. We denote it by C of XA, which is the space of all continuous functions defined in a completely regular space X with values in E, where A is a topological vector space. Well, under some special conditions, this space is actually an algebra. And many authors have studied the subalgebra consisting of all bounded continuous functions defined on X, and with values in A, where A can be a Banach algebra or a more general topological algebra. There is another important subalgebra of C of XA, which is the main object of this talk. And this subalgebra is the one that you can see on the screen, CV not of XA. And what I will do is to present some results that this is a joint work with two colleagues, and this is we have worked for maybe a couple of years and studied what happens in this algebra. Well, if this X is a completely regular space, and V is a Natchmen family on X that I'm going to define, I'm just about to define, and A is a locally convex algebra, we will denote CV0 of XA to the algebra of all continuous weighted vector-valued functions defined on X. So what I will do is to present some of the properties of this function algebra that are inherited by the corresponding properties in A. These are related to M convexity, locally uniformly A convexity, completeness, and projective limits, and the Arens-Michael decomposition. And this Aaron's microdecomposition is, in fact, one of the main tools in the study of complete M-convex algebras. And it expresses, the importance of this is because it expresses the algebra we are studying as the limit algebra of a projective system of normed or Banach algebras. And what is the main point in doing this? The main point is that then, as we know, a lot of properties that characterize Banach algebras, for example, we can analyze what is happening in the algebra that we are interested in. So I will start with the previous definitions. A topological algebra is a complex algebra A endowed with a house of linear topology tau in which the multiplication is separately continuous. And a topological algebra A tau is a locally convex algebra if tau is a locally convex topology. And in this case, the topology is defined by a family of seminorms that in the sequel you will note that I will be writing P lambda, this family, in this way. Well, everybody knows what a complete irregular space is, and we have examples of this kind of C of XA, for example. If X is a completely regular Hausdorff space, and if A with the family of seminorms is a locally convex algebra, then C of XA, which is the space of all continuous functions defined on X with values in A, is a locally convex space when it is endowed with the following seminorms that you can see over here. For each alpha in I, we define this family of seminorms of F as the supremum of this set for F in C of XA. So now we are going to consider that X is a completely regular Hausdorff space and V a family of upper semi-continuous non-negative functions on X. We say that V is a Nachman family if it satisfies these three properties. The first one says that for every X in X, there is a V in V such that V of X is greater than 0. The second one says that for every V in V and lambda a positive number, we have that this multiple of V is in V. And the third one says that if we have a pair, if we have B1 and B2 in V, there is always another element in V such that it majorizes B1 and B2. And from now on, we will also suppose that for every V, in V, V will be different from 0. For every V in V, we will denote by NV to the set of all elements in X, such that N of V of X is positive. And moreover, we will say that V satisfies the BB property, and BB property was a name that we chose for this property because it means bounded below. So, moreover, V satisfies the BB property if for each X in X, there are a V in V, a neighborhood UX of X, and a positive number M such that M is smaller or equal to V of Y for every Y in UX. Okay, so who is this space that we have talked about since the beginning? If X is a completely regular Hausdorff space and V is a Nachman family on X, and we have that this is a locally convex algebra, CV0 of XA is the set of all F of all functions in C of XA, such that this product vanishes at infinity for every V in V and every alpha in I. This is a vector space with the usual operations for vector-valued functions. And the first thing that I would like to point out about this vector space is that it is not always a topological algebra. So we need something more in order to assure that CV naught of XA can be an algebra, a topological algebra. So we define the following seminorms on CV0 of XA. For alpha in I and V in V, the alpha B seminorm of F is the supremum of this product, where X is in X, and this happens for each F in CV naught of XA. So CV naught of XA with this family of seminorms is a locally convex space. And when A is the complex numbers, well, we usually write CV naught of X instead of CV naught of XC. We have some examples. Let's consider V, the set of all constant positive functions on X. Then CV naught of XA is the space of continuous vector valued functions of vanishing at infinity. Or if V is the set of these products where lambda is positive, and this is the characteristic function on compact subsets of X, then CV naught of XA is the algebra of all vector valued continuous functions with the topology of uniform convergence on compact subsets of X. Or, for example, I will choose one of these. If X is a locally compact space and V is a set of positive real valued continuous functions on X, CV naught of X is the algebra of continuous unbounded complex valued functions with a strict topology. Latvik Ubi from Morocco proved in 1998 that under certain conditions on X and A, the locally convex space that I just defined is actually a locally convex algebra. And these conditions are the two following ones. The first one says that for every X in X, there is a V in V, such that the set that you can see here in NV, which is equal to this, the set of LX in X, such that V of X is positive, is a neighborhood of X. And the second is that A is of these sets with this condition. And this means, to be hypotopological, FV0 hypotopological, this means that for every alpha in I and for every V in FB and FB naught, there is a beta in I and M, a positive number M, such that the maximum of this set is less or equal than this product for each B in B and A in A. So we will always assume that these conditions hold because we are interested in studying this algebra. And these are the conditions that I said before that are needed in order to have this and a locally convex algebra. Okay, well, the first thing that we found is that if X is a completely regular Hausdorff space and A with this family of seminorms is a locally convex algebra with identity E, then the following conditions are equivalent. The constant function 1 is in CV naught of X. Second, every V in V vanishes at infinity. Third, CV naught of XA has an identity. So For example, I will talk about some properties that are preserved, that are inherited. A locally M-convex algebra is a locally convex algebra, E, whose topology is defined by a family of seminorms, P lambda with lambda and lambda, which satisfies the condition that you see over here for all x and y in E. And the first result that I would like to present today is that if X is a completely regular Hausdorff space, and A is an M-convex algebra, and if CV naught of X is an M-convex algebra, then CV naught of XA is also M-convex. So you see here A M-convex, and if this happens, then CV naught of XA is also M-convex. Reciprocally, if A has a unit E and CV naught of XA is an M-convex algebra, then CV naught of X is also an M-convex algebra. Now, another property deals with completeness. If X is a completely regular Hausdorff space and A is a complete or sequentially complete locally convex algebra, and if B satisfies the BB property, then CV naught of XA is a complete, sequentially complete locally convex algebra. So you see here we have complete or sequentially complete, and then we have that CV naught of XA is complete or sequentially complete locally convex algebra. So what about uniformly A convexity? Well, a locally convex algebra here's missing one parenthesis, is locally uniformly A convex if for each X in A, there is a positive number that depends on X, such that the maximum of these two is less or equal than this product for every Y in A and alpha in I. And what do we know about uniformly A convexity? Well, if X is a completely regular Hausdorff space and A is a sequentially complete locally uniformly A convex algebra with unit E, if CV naught of X is a locally uniformly A convex algebra, then CV naught of XA is a locally uniformly A convex algebra as well. Well, now here comes the definition of projective systems. If we have this a directed set and this a family of complex topological algebras and continuous homomorphisms like the one that I have here, phi alpha beta that goes from A beta to A alpha for every alpha less or equal than beta. And if we suppose that this composition is this whenever alpha is less or equal than beta and less or equal than gamma, and phi alpha alpha is the identity in A alpha for every alpha, then this system with this family of morphisms is called a projective system of topological algebras. So the projective limit algebra of this projective system is defined as the pair that you can see here, a projective limit of A alpha with this family of morphisms. And well, I just recall that this projective limit is a subset of the direct product. And so phi alpha that goes from the projective limit of A alpha to A alpha is defined as follows for every element in the projective limit A alpha. And the topology in the projective limit is the initial topology defined by the maps, these maps, that is the weakest topology on the projective limit such that each phi alpha is continuous. Okay, why do I have to deal with this? Because I am just about to recall what the Arens-Michael decomposition is and to see what happens in our special case. Now, if we have this a complete locally M-convex algebra, for each alpha in I, we define the algebra A alpha as this quotient, the completion of this quotient. And for alpha and beta in I, we define alpha less or equal than beta if and only if P alpha of X is less or equal than P beta of X for every X in A. So for alpha less or equal than beta, we define the homomorphism phi alpha beta that goes from A beta to A alpha. And it is the continuous extension of the canonical homomorphism that does this. It can be proved that this algebra, this one, with this family of morphisms, is a projective system, and that A is isomorphic to the projective limit of A alpha. And that's what we call the Arens-Michael decomposition. So as you see, these alpha now are Banach algebras, in fact. So what we found out is that if we have a complete locally M-convex algebra and it is isomorphic to the projective limit, and this is its Arens-Michael decomposition, where each A alpha is the completion of this quotient, then CV naught of XA is exactly the projective limit of CV0 of X A alpha within an isomorphism of topological algebras. And what we do is to analyze how these things work in order to have more general solution, answers to the structure of CV naught of XA. There are many other properties that I could point out, but it's a long way to go, and I don't know, but I think that my time is already finished. So I would just present part of the references that we used in order to do so. And thank you very much for your attention.
Thank you very much, Professor Lutz, for your nice talk and nice explanation. Are there any questions? Any questions? So let's thank again, Professor Lutz, for your talk.
Thank you so much.
Thank you so much for coming. So then we finish the second day of our section. Then let's remind all of you that the lectures tomorrow will start at 8:30 a.m. at CD time. And today is the last day of the conference. Okay, thank you. Thanks everyone for coming. I hope to see everyone tomorrow. Maybe Professor Javier wants to say something? No?
Thank you very much, Carol.
Thank you, Professor. Mucho gusto. Thank you. Ahoy, Milan.
Ahoy, Carol.
Ahoy, Milan. Hope you are fine.
Goodbye. Goodbye.
Goodbye. Goodbye.
Bye.
Thank you, Professor
Goodbye.
Lourdes, again. Goodbye. Thank you for your help today. Thank you. Thank you. See you, all of you, tomorrow. Thank you. Bye, Milan.
Bye-bye. Somehow